Look up at the night sky on a clear, dark evening, and what you see is a breathtaking, yet deceptive, stillness, a scattering of diamond-like points of light against a velvet black. But that serene view is only the barest whisper of the universe's true scale and nature. What our eyes perceive as a single, steady star might in fact be a swirling galaxy of billions of suns, a colossal nebula where new stars are being born, or the ghostly remnant of a stellar explosion that happened millennia ago. For centuries, astronomers have sought to catalogue this cosmic menagerie, to bring order to the celestial chaos, and their greatest effort in this pursuit is the new General Catalogue, or the NGC. This immense catalogue is a map to over 13,000 deep sky objects, a treasure trove of cosmic wonders that are, for the most part, invisible without the aid of a powerful telescope. It's a directory to the universe's most stunning and bizarre residents. Yet, within this vast catalogue of galaxies, nebulae, and star clusters, there exists a collection of objects that stand apart. These are not your typical, well-behaved cosmic phenomena. They are the outliers, the anomalies, the celestial curiosities that defy our current understanding of physics and challenge our very definitions of reality. We're about to embark on a journey to explore 50 of these strange and mysterious objects from the NGC. We will encounter cosmic whirlpools that seem to spin in impossible ways, ethereal clouds that glow with no clear source of energy, and structures so vast and perfectly shaped they seem almost artificial. These are not just beautiful sights, they are profound puzzles, each one a piece of a much larger cosmic mystery waiting to be solved. This is more than just a tour of strange sights, it is an exploration into the very limits of human knowledge. Every one of these 50 objects whispers a question that we have yet to fully answer. They spark a fundamental curiosity that connects us to every human who has ever looked up at the heavens and wondered what lies beyond. They remind us that the universe is far stranger, more violent, and more wonderful than we could ever imagine from our tiny vantage point. So prepare to have your perspective shifted and your sense of wonder reignited as we begin our countdown of 50 strange objects in the NGC that continue to baffle and inspire astronomers to this day. And so we begin our journey into the strange with an object that seems almost alive, a cosmic chameleon that alters its appearance right before our eyes. At first glance, number 50 on our list, NGC 2261, also known as Hubble's Variable Nebula, looks like a fairly typical fan-shaped nebula, a delicate, glowing comet-like structure located in the constellation Monoceros. But its beauty hides its true nature. This is not a static cloud of gas and dust, it is a dynamic, shifting entity. Over a matter of just weeks, its shape can warp, its brightness can fluctuate, and its intricate details can appear to shift and swirl. This remarkable variability was first documented in detail by the legendary astronomer Edwin Hubble in the early 20th century, cementing its place as one of the most peculiar and closely watched objects in the sky. So what could possibly cause an entire nebula, a structure light years across, to change so rapidly? The secret lies not within the nebula itself, but with its fiery, hidden heart, a very young and violent star known as R Monocerotis. This isn't a calm, steady star like our Sun. R Monocerotis is a stellar infant, shrouded in a thick, rotating disk of gas and dust from which it was born. This disk is tilted in such a way that it blocks our direct view of the star itself, but the star is tremendously active, firing off powerful jets of material and experiencing intense, chaotic outbursts. The leading theory suggests that the variability we see is a grand-scale shadow play. As massive, dense clumps of dust orbit within this disk, they cast enormous, moving shadows out into the surrounding nebula. These shadows, stretching across trillions of miles, are what we perceive from Earth as the nebula's changing shape and brightness. It's as if a cosmic hand is moving in front of a colossal flashlight, creating a dynamic light show on an interstellar screen. This makes Hubble's variable nebula a unique natural laboratory, allowing us to observe the tumultuous processes of star formation in almost real time, witnessing the birth pangs of a sun and the profound influence it has on its newborn environment. Moving deeper into our cosmic catalogue of curiosities, we arrive at a celestial spectre that has both haunted and delighted sky watchers for generations. At number 49 on our list is NGC 3242, famously known as the Ghost of Jupiter. This planetary nebula, located in the constellation Hydra, presents an almost perfect glowing blue-green disk that, when seen through a telescope, bears an uncanny resemblance to the giant planet in our own solar system. But this is no world. What we are witnessing is the final, beautiful death throes of a star once very much like our own sun. After exhausting its nuclear fuel, the star cast off its outer layers into space, creating a magnificent, glowing shell of ionized gas that now expands outward, illuminated by the intense ultraviolet radiation from the tiny, hot stellar corpse left at its center, a white dwarf. The intricate structures within this cosmic ghost are what truly captivate astronomers. Through powerful telescopes like Hubble, we can see that the nebula is not a simple, smooth bubble. It consists of multiple, complex shells of gas. The bright inner shell, the part that gives it its eye-like appearance, is surrounded by a much larger, fainter halo of material that was likely ejected by the star in an earlier red giant phase. Delicate, jet-like structures stream from the poles of the central star, suggesting that the entire system may be shaped by powerful magnetic fields or the gravitational influence of an unseen companion star. This layered complexity tells a story of a star's death that was not a single, simple event, but a series of dramatic outbursts and transformations over thousands of years. The fate of the star's core is as fascinating as the nebula itself. The white dwarf remaining at the heart of NGC 3242 is an incredibly dense object, packing a mass comparable to our Sun's into a volume no larger than Earth. It is now a slowly cooling ember, destined to fade over billions of years. This entire system serves as a stark preview of our own solar system's distant future, a vivid illustration of the eventual fate that awaits the Sun and, by extension, the Earth. It's a humbling and awe-inspiring thought that this beautiful, ghostly apparition is a window into a future 5 billion years from now. For amateur astronomers, the Ghost of Jupiter holds a special place as one of the brightest and most accessible planetary nebulae in the night sky. Even with a modest telescope, its vivid, bluish disk is readily visible, a testament to its high surface brightness. Its relative ease of finding and its striking, planetary-like appearance make it a premier target for backyard stargazers, a direct and personal connection to the profound cosmic cycles of stellar life and death. It stands as a perfect example of how an object of immense scientific importance can also be a thing of sheer, breathtaking beauty, a celestial tombstone that is as haunting as it is illuminating. But to find true cosmic violence on a galactic scale, we need to look beyond the ghostly remnants of dead stars to places where entire worlds are being reshaped. At number 48 and 47 on our list, we find two galaxies, NGC 5128 and NGC 1316, that serve as stunning testament to the universe's most destructive and creative force, the colossal collision of galaxies. These are not the serene, spinning pinwheels you might picture. These are cosmic train wrecks, and the wreckage tells an incredible story. First, let's turn our gaze to NGC 5128, better known to astronomers as Centaurus A. Even in a small telescope, this galaxy is an immediate oddity. It presents as a bizarre hybrid, a massive, fuzzy elliptical galaxy brutally bisected by a thick, jagged, and incredibly dark lane of dust. This dramatic feature is the first clue to its violent past. Astronomers are now certain that Centaurus A is the product of a dramatic merger, where a large elliptical galaxy cannibalized a smaller, gas-rich spiral galaxy. That iconic dust lane is the shredded remains of that spiral galaxy, now being consumed and incorporated into the larger elliptical. It's a snapshot of a cosmic meal still in progress, a temporary scar from a gravitational encounter that happened hundreds of millions of years ago. The drama of Centaurus doesn't end with its striking visual appearance. Peering deeper with radio and X-ray telescopes reveals an even more energetic secret. At its very core lies a supermassive black hole, weighing in at about 55 million times the mass of our Sun. The immense inflow of gas and dust from the galactic merger has supercharged this black hole, turning it into an incredibly powerful engine. This active galactic nucleus is firing out colossal jets of subatomic particles at nearly the speed of light, stretching for over 1 million light-years into intergalactic space. These jets, invisible to our eyes but brilliant in radio waves, make Centaurus one of the closest and brightest radio galaxies in our sky. It is a multi-wavelength powerhouse, a direct result of a violent merger that not only reshaped a galaxy but also awakened a sleeping giant at its heart. Not far from Centaurus A, both in the sky and in the annals of strange galaxies, lies our number 47, NGC 1316. At first glance, it shares a family resemblance with its chaotic neighbor. It's another massive elliptical galaxy, but a closer look reveals its own unique scars of a turbulent history. Surrounding its bright core are intricate, wispy loops and delicate shell-like structures, faint arcs of stars that seem to be draped around the galaxy like layers of a cosmic onion. These tidal shells are the unmistakable calling card of a past merger. They are the ghosts of a smaller galaxy that was torn apart and absorbed, with its stars now scattered into vast, orbiting streams that we see as these delicate ripples. The process is a gravitational echo, a reminder of a smaller system that was utterly dismantled and consumed. NGC 1316 also shows evidence of containing vast but unusually positioned clouds of dark, complex dust lanes, similar to but less prominent than the one in Centaurus A. This suggests it, too, merged with a gas-rich spiral galaxy, funneling that material inward. And just like Centaurus A, this influx of fresh fuel appears to have ignited activity at its core. NGC 1316 is also classified as a radio galaxy, home to its own active supermassive black hole, though its jets are not quite as powerful as those of its more famous neighbor. What makes this galaxy particularly compelling for astronomers is that it sits at the center of a sprawling cluster of galaxies known as the Fornax cluster. Its sheer size and its central location suggest that it may have grown to its current dominant state through not just one, but a series of multiple mergers over billions of years, a process known as galactic cannibalism. It stands as a stark reminder that even the largest structures in the universe are not immutable. They are shaped and built by a relentless history of collision and consumption. Together, Centaurus A and NGC 1316 show us that galactic mergers are not merely destructive events. They are fundamental to the evolution of the universe, triggering the birth of new stars, feeding the monsters at galactic centers, and building the giant elliptical galaxies we see today. Our journey through the strange and wonderful now brings us to one of the most fertile stellar nurseries in our entire galactic neighborhood, the Great Orion Molecular Cloud Complex. Within this sprawling tapestry of gas and dust lie three particularly intriguing entries in the NGC Catalogue, each presenting its own unique cosmic riddle. First among them, at number 46 on our list, is NGC 1999. When first imaged by the Hubble Space Telescope, this reflection nebula appeared as a beautiful, keyhole-shaped cloud of dust, glowing with the reflected light of the brilliant young star V380 Orionis embedded within it. But the most striking feature was a bizarre, triangular black patch right next to the star, a region of profound darkness that seemed to be a classic Bok globule, a dense, cold cloud of gas and dust so thick it blocks all background light. For years, that's exactly what astronomers believed it was, But then came further observations, particularly from the European Space Agency's Herschel Space Observatory, which was designed to peer into such cold, dense regions. To the astonishment of the scientific community, Herschel saw nothing. The dark patch was not a dense, star-forming globule. It was, in fact, a vast and truly empty cavity. Somehow, the powerful radiation and fierce stellar winds from the newborn star V380 Orionis, and likely from other massive stars in the vicinity, had blasted away the gas and dust in that region, carving out a hole in the nebula and leaving behind a void. This discovery transformed NGC 1999 from a simple pretty picture into a profound example of the destructive and shaping power of young stellar objects, revealing that the emptiness itself can be as scientifically significant as the glowing clouds. Just a short cosmic distance away, we find our 45th strange object, NGC 2024, the magnificent Flame Nebula. Situed ominously close to the leftmost star of Orion's belt, Alnitak, this nebula is a colossal cloud of glowing hydrogen, energized into a brilliant emission state. From a distance, it truly does resemble cosmic flames licking at the sky, with dark, intricate tendrils of dust creating a dramatic, smoky appearance. But the visible fire is only part of the story. The intense ultraviolet radiation that sets the gas ablaze doesn't come from Alnitak alone. Hidden deep within the central dark dust lane is a tight cluster of young, hot stars completely obscured from our optical view. It is this hidden cluster that is the true engine of the Flame Nebula. Their powerful light is what ionizes the surrounding hydrogen, making it glow, while their fierce winds are simultaneously sculpting and eroding the very dust cloud that birthed them. This creates a dynamic and violent environment, a constant struggle between the forces of gravity pulling material together and the stellar radiation blowing it apart. Observing the Flame Nebula in different wavelengths, like infrared light, allows us to peer through the obscuring dust and see the stellar nursery within, giving us a front-row seat to the earliest, most chaotic stages of a star cluster's life. It's a vivid demonstration that the most energetic processes in the universe are often hidden in plain sight, shrouded by the very material from which they were born. Completing this Orion trio is number 44, NGC 2071. While less famous than its flashy neighbors, this nebula is a hotbed of extremely active and youthful star formation. It is classified as a reflection nebula, but it's far from a peaceful scene. Within its dusty confines, a small cluster of newborn stars is unleashing tremendous amounts of energy. The most dramatic evidence of this is the presence of powerful bipolar molecular outflows, twin jets of gas being ejected at supersonic speeds from the poles of the protostars buried deep within the cloud. These outflows are a universal signature of star birth. As a dense core of gas collapses to form a star, it spins faster and faster, flinging excess material away along its magnetic poles in incredibly focused beams. These jets can stretch for light years, slamming into the surrounding interstellar medium and creating shock waves that heat the gas and make it glow. In NGC 2071, these outflows are particularly prominent, visible to radio telescopes as vast lobes of energized molecules. Studying this system provides a critical window into the feedback processes that regulate star formation. The outflows essentially clear away the surrounding material, determining the final mass of the new star and potentially shutting down the formation of additional sibling stars nearby. These three nebulae in Orion, the void of NGC 1999, the hidden fires of the flame, and the violent birth cries of NGC 207, together paint a comprehensive and dynamic portrait of the complex, turbulent, and beautiful life cycle of stars. Now, shifting our gaze from the vast stellar nurseries of Orion, we encounter one of the most visually arresting and structurally complex planetary nebulae in the heavens. At number 8 on our list of strange objects is NGC 2392, popularly known as the Eskimo Nebula. When viewed through a powerful telescope, its resemblance to a face surrounded by a furry parka hood is so striking it's almost uncanny. That bright central core looks like a pair of eyes and a mouth, while the surrounding, fainter shell of gas creates the illusion of thick fur trim. But this beautiful, almost playful appearance is the result of some of the most violent and finely tuned physical processes in the universe, the death of a star choreographed with stunning precision. The story of the Eskimo Nebula begins with a star very similar to our Sun, approaching the end of its life. After billions of years of stable nuclear fusion, it exhausted the hydrogen fuel in its core and began to swell into a red giant. During this turbulent phase, the star started to shrug off its outer layers, but it did so in distinct and separate outbursts. The first event was a relatively slow and dense outflow of material, which expanded outward to form the large, faint, spherical halo that we now see as the nebula's parka. This initial shell of gas drifted away from the star for centuries, creating a vast, tenuous bubble in space. Then the drama intensified. The exposed core of the star, now a white dwarf, heated up to incredible temperatures, becoming a source of intense ultraviolet radiation. At the same time, this newly born white dwarf began ejecting a second shell of gas, but this time the outflow was radically different. It was a fast wind, a torrent of particles streaming away from the star at speeds millions of miles per hour. This high-speed wind soon caught up with the older, slower-moving shell, and when it did, it plowed into it like a supersonic snowplow. The collision was spectacular. The fast wind compressed the inner edge of the slower shell, piling the gas up into a dense, bright rim. The intricate structures we see within that central bubble, the complex loops and the filamentary patterns that look like a face, are the direct result of this interaction. They are essentially shock fronts and instabilities frozen in gas, a snapshot of a titanic collision between two stellar winds. What adds another layer of complexity to the Eskimo Nebula, and what truly makes it a standout object for astronomers, is the remarkable symmetry and fine detail of its inner structure. It's not a simple, smooth disk. The central region is filled with what appear to be comet-like knots of dense gas, all with their tails pointing radially away from the central star. These are not small features. Each one is roughly the size of our entire solar system. The prevailing theory is that these knots formed as the outgoing blast wave from the central star crashed into denser, lumpy regions within the earlier, slower wind. The intense radiation from the white dwarf then sculpted these lumps, eroding the material on the side facing the star and creating the long, trailing tails. This gives the inner nebula its extraordinarily textured, almost fuzzy appearance, as if it were indeed made of cosmic fur. The central face itself, with its two bright areas that look like eyes, is likely an effect of our line of sight perspective. We are peering through a thick, barrel-shaped structure of gas. The bright areas are regions where we are looking down the long axis of this structure, seeing deeper into the brighter central regions, while the darker areas are where our view is blocked by the walls of the barrel. This intricate geometry is further influenced by the possibility of a binary companion star or a powerful magnetic field around the central white dwarf, which could focus the outflows and create the pronounced bipolar structure. The Eskimo Nebula, therefore, is far more than a pretty picture. It is a fossil record of a star's final, gasping breaths, a dynamic laboratory showing us how momentum and energy transfer through interstellar space, and a humbling preview of the artistic and violent fate that awaits our own sun billions of years from now. Sometimes the universe creates structures of such breathtaking complexity and symmetry that they seem to defy natural explanation. This is certainly the case for our number 9, NGC 6543, the legendary Cat's Eye Nebula. Located in the constellation Draco, this planetary nebula is arguably the most intricate and finely detailed object of its kind ever discovered. Through a telescope, it doesn't appear as a simple, round bubble like many of its cousins. Instead, it reveals a stunning, layered structure, a brilliant, elliptical inner core crisscrossed by a bright central bar, all surrounded by a series of faint, perfectly concentric rings of gas that look like the ripples from a stone thrown into a cosmic pond. It is a celestial masterpiece, a work of art on a scale of trillions of miles, and its beauty is a direct reflection of the incredibly violent and complex death of its central star. The first and most obvious puzzle of the cat's eye is the series of those concentric shells. Astronomers have counted at least 11 of these nearly perfect spherical halos expanding outward from the central star. For a dying star to produce such a regular, onion-like structure, it couldn't have ejected its outer layers in a single, continuous eruption. Instead, the prevailing theory suggests that the star experienced a series of distinct rhythmic pulses. Roughly every 1,500 years, the star underwent a massive, albeit relatively gentle, outburst, ejecting a shell of material into space. This process repeated over millennia, with each new shell expanding into the void left by the previous one. What could cause such a precise, clockwork-like series of hiccups in a dying star? The mechanism is still debated, but it likely involves periodic instabilities deep within the star's helium-burning shell, causing it to flare up and gently push the star's atmosphere outward at regular intervals. Yet the concentric shells are only part of the story. The very center of the cat's eye is a maelstrom of activity that stands in stark contrast to the serene, expanding rings. Here we see a bright, elongated inner nebula, shot through with high-speed jets of gas that blast outward in opposite directions, as well as intricate knots and shock-heated filaments. This central region is the result of a much more recent and powerful event, the final, violent ejection of the star's remaining outer envelope. This material was expelled at tremendous speed, and when it slammed into the older, slower-moving shells, it created the complex shock fronts and glowing structures we see today. So we have two distinct phenomena superimposed: the slow, rhythmic pulse of the shells and the fast, explosive finale that sculpted the inner eye. This combination of a gradual, pre-programmed decline and a sudden, terminal cataclysm makes the cat's eye a unique historical document, chronicling the final millennia of a star's life in exquisite detail. This leads to the central mystery: what orchestrated this intricate dance of creation? How could a single star manage to produce both perfectly spherical shells and highly directional, jet-like structures simultaneously? The most compelling answer points to a cosmic duet. Astronomers strongly suspect that the central star of the cat's eye is not alone. It is likely part of a binary star system. In this scenario, the primary star, the one that died and became the white dwarf we see today, had a companion star orbiting closely around it. As the primary star swelled into its red giant phase, its outer atmosphere would have enveloped the smaller companion star. The gravitational tug of war between the two stars would have created immense tidal forces, effectively spinning up the giant star's envelope and channeling its ejections. The companion star's gravity could have acted like a sculptor's tool, focusing the final, fast outflow into the powerful bipolar jets we observe, while the earlier, slower pulses remained largely spherical, creating the iconic concentric rings. The evidence for this binary model is mounting. Observations have revealed that the central white dwarf is one of the hottest stars known, with a surface temperature exceeding 80,000 degrees Celsius, and it is rotating extremely rapidly and has a powerful magnetic field. Both rapid rotation and strong magnetic fields are much easier to explain if the star was spun up by a close companion, while a direct detection of this second star has proven elusive. Hidden within the glare of the brilliant white dwarf, the intricate architecture of the entire nebula points strongly to its influence. The Cat's Eye Nebula, therefore, stands as a profound example of how binary star interactions can shape the death of a star, transforming what might have been a simple, expanding sphere into one of the most complex and beautiful structures in the cosmos. It is a stunning reminder that the universe's most magnificent artworks are often born from the most dynamic and violent relationships. But even the intricate artistry of the cat's eye pales in comparison to the sheer architectural strangeness of our next object. At number 10 on our list, we encounter NGC 7009, the astonishing Saturn Nebula. Located in the constellation Aquarius, this planetary nebula earns its name not from the rings of Saturn, but from a far more bizarre and rare configuration. When observed through a substantial telescope, it presents a bright, elongated central body flanked on either side by two distinct, handle-like protrusions known to astronomers as ansae. This gives the entire structure an uncanny resemblance to the ringed planet as it might appear through a small telescope with the rings seen edge-on. Yet these are not rings at all. They are isolated, glowing blobs of gas positioned far out from the nebula's core, and their existence points to one of the most dynamic and violent processes in the late stages of stellar evolution. The central mystery of the Saturn Nebula has always been the nature of these enigmatic ansae. How could a dying star produce such perfectly symmetrical yet disconnected structures? The answer lies in the ferocious activity of the nebula's central star, a brilliant white dwarf that is one of the hottest stars known, with a surface temperature soaring to an incredible 55,000 degrees Celsius. This stellar remnant is not shining peacefully. It is blasting the surrounding space with a torrent of ultraviolet radiation and, more importantly, propelling material outward at phenomenal speeds. Observations from the Hubble Space Telescope have been crucial, revealing that the central star is firing off narrow, collimated jets of gas at velocities approaching hundreds of kilometers per second. These are not the gentle, spherical winds of the initial ejection phase, but are more akin to ultra-powerful cosmic fire hoses. The prevailing theory for the formation of the ansae is a dramatic story of interaction and collision. It is believed that these high-velocity jets streaming out from the poles of the central star have plowed directly into the older, slower-moving shell of gas that was ejected earlier in the star's death throes. The jets essentially punched through the ends of the main elliptical shell, carrying material far beyond its boundaries. The ansae we see today are the glowing, shocked remnants of that interaction, the endpoints where these jets were finally stopped and their energy dissipated, lighting up like celestial exclamation points. This process created the iconic handles and also sculpted the nebula's intricate inner structure, which Hubble reveals to be a complex arrangement of elongated shells, knots, and filaments. The entire system looks less like a simple bubble and more like a piece of elaborate ethereal machinery. This model strongly suggests that the central engine of the Saturn Nebula is far from simple. To produce such focused, high-speed jets, there must be a mechanism to collimate the outflow, to squeeze it into tight beams. As with the Cat's Eye Nebula, the most likely culprit is a binary companion star. The gravitational influence of a second star orbiting the primary could have funneled the outflows along the system's rotational axis, creating the precise jets needed to form the ansae. Alternatively, an incredibly powerful magnetic field around the white dwarf could have channeled the material. While direct evidence for a companion remains elusive, the nebula's complex geometry all but demands it. The Saturn Nebula, therefore, stands as a brilliant testament to the transformative power of stellar jets. It shows us that the final stages of a star's life are not a quiet fading, but can be a period of intense, focused activity that carves and shapes the surrounding interstellar medium into forms of stunning and lasting beauty. It's a celestial sculpture where the chisels are beams of gas moving at a fraction of the speed of light. Now we venture into a realm where the very act of observation creates a magical illusion, a celestial sleight of hand that has fascinated amateur astronomers for over a century. Our next two strange objects, NGC 6826 and NGC 7662, are known collectively as the blinking planetary nebulae, on their own, each is a beautiful and scientifically fascinating shell of gas, but it is the unique interaction between their structure and the human eye that elevates them to legendary status. The experience is simple yet utterly captivating. When you look directly at one of these nebulae through a telescope eyepiece, you often see only the brilliant, star-like point of its central white dwarf. But the moment you shift your gaze slightly away using averted vision, the faint, glowing nebula itself suddenly pops into view, seeming to materialize out of nowhere. Shift your gaze back and the nebula vanishes, leaving only the central star. It's as if the universe itself is winking at you, a phenomenon that never fails to elicit a gasp of wonder from first-time observers. To understand why this happens, we need to delve into the peculiarities of our own vision. The human retina is not uniformly sensitive to light. At its very center lies a small region called the fovea, which is packed with cone cells responsible for our high-resolution color vision in bright light. However, these cones are not very sensitive to faint, extended objects. The rod cells, which are far more sensitive to low light levels, are concentrated in the areas surrounding the fovea. So, when you look directly at a blinking planetary nebula, you are placing its faint, extended glow onto the relatively insensitive fovea, causing it to disappear. But when you look slightly to the side, you project that same faint light onto the rod-rich periphery of your retina, which instantly detects it, making the nebula appear as if by magic. This stark contrast between the intensely bright central star and the much fainter nebula is the perfect recipe for this visual trick, a beautiful demonstration of how our own biological limitations can create profound cosmic illusions. Our first blinking wonder, NGC 6826, also bears the evocative nickname, the Blinking Planetary. Located in the constellation Cygnus, this nebula presents a more complex structure than the simple blinking effect might suggest. Through a large telescope, when the nebula is held steady in view, it reveals a bright, oval-shaped inner shell that appears to have a vibrant greenish-blue hue, a color caused by the intense emission of doubly ionized oxygen atoms. But what truly sets NGC 6826 apart are two brilliant, red, fast low ionization emission regions, or flyers, located on opposite sides of the main shell. These appear as small, compact knots, and their composition and high speed suggest they were ejected later in the nebula's formation, likely as high-velocity jets from the central star. This combination of a bright inner ellipse and these symmetrical, high-speed knots makes it a dynamic object, a nebula that experienced multiple distinct outbursts in its final death throes. The central star itself is a notable feature, shining at a magnitude bright enough to easily drown out the surrounding gas and create that perfect blinking scenario, making it one of the most popular and accessible demonstration objects in the northern sky. Our second object, NGC 7662, is often called the Blue Snowball Nebula, found in the constellation Andromeda. While it also blinks dramatically, its structure is subtly different. Through sustained observation, it resolves into a remarkably well-defined, crisp blue disk. This intense blue-green color is even more pronounced than in NGC 6826, again due to the strong emission from oxygen. High-resolution images from the Hubble Space Telescope reveal an incredibly intricate inner structure that belies its simple, snowball-like appearance through smaller telescopes. It consists of a bright, elongated inner ring surrounded by a fainter, more diffuse outer halo. Delicate radial filaments and ansae, similar to but fainter than those in the Saturn Nebula, speak to a complex ejection history involving multiple shells and possibly bipolar outflows. The central star is incredibly hot, with temperatures estimated to be over 75,000 degrees Celsius, providing the fierce ultraviolet radiation that makes the entire nebula fluoresce so brilliantly. The stark contrast between this searingly hot pinprick of light and the fainter, extended glow of the oxygen-rich gas creates a blinking effect that is every bit as pronounced as its counterpart in Cygnus. Scientifically, these two nebulae are more than just visual curiosities. They are textbook examples of what astronomers call high-excitation planetary nebulae. The sheer temperature of their central stars means they are emitting copious amounts of the specific high-energy ultraviolet light needed to strip two electrons from oxygen atoms, causing them to glow with that characteristic greenish-blue light that dominates their appearance. Their similar blinking behavior is a direct result of this shared physical property, a very hot, bright central source juxtaposed against a fainter, oxygen-rich nebula shell. Studying their detailed structures, from the flyers in NGC 6826 to the intricate inner rings of the blue snowball, provides critical data for understanding the final, rapid evolutionary phase between a red giant and a white dwarf. They represent a brief, brilliant splash of color in the life cycle of a star, a phase that lasts only a few tens of thousands of years before the nebula dissipates into the interstellar medium and the white dwarf slowly cools for eons. So the next time you hear an astronomer speak of a blinking planetary, you'll know they are describing a beautiful partnership between the precise physics of a dying star and the wonderful quirks of human perception, a cosmic dance where seeing is not always believing. From the delicate blinking illusions of our last stop, we now turn to witness a cosmic spectacle of almost unimaginable violence and scale, a dying star that has unfolded wings of fire across the void. At number 13 on our list of strange objects is NGC 6302, the breathtaking Butterfly Nebula. Located in the constellation Scorpius, this is a planetary nebula that defies all expectations of serene, spherical endings. Instead, it presents one of the most extreme examples of a bipolar nebula, with two vast, symmetrical lobes of gas expanding outward from a central waste of dense dust. The sheer size of this structure is staggering. From wingtip to wingtip, this celestial insect spans over 3 light years, a distance that would take a beam of light, the fastest thing in the universe, more than 3 full years to cross. To put that in perspective, if you place this nebula at the center of our solar system, its wings would extend far beyond the orbit of the nearest star, Proxima Centauri. This is not a gentle death. It is a stellar explosion channeled into a form of breathtaking, terrifying beauty. The extraordinary shape of the Butterfly Nebula is a direct consequence of the ferocious activity at its heart. Hidden within a thick, dusty torus or donut-shaped ring, at the nebula's center is one of the hottest stellar objects ever discovered. This central engine is a white dwarf star with a surface temperature that is almost incomprehensible, estimated to be around 250,000 degrees Celsius. To grasp that number, consider that the surface of our own Sun is a comparatively cool 5,500 degrees. This remnant star is so intensely hot that it shines with a brilliance that is overwhelmingly in the ultraviolet part of the spectrum, a light our eyes cannot see but which provides the raw power that makes the entire nebula flourish. The reason the nebula has its iconic winged shape is that this thick central dust disk is acting like a nozzle, channeling the star's intense radiation and powerful stellar winds. Rather than expanding in all directions equally, the material is forced to flow outward above and below the disk, inflating the two gigantic lobes we see as wings. This creates a stunning contrast. The dark, cold central belt obscures our direct view of the star, while the glowing lobes testify to the incredible energy blasting through the only available exits. But the drama of the Butterfly Nebula extends far beyond its visible structure. When astronomers have analyzed the chemical composition of its wings using spectroscopy, they have uncovered a truly exotic environment. The ejected material is incredibly rich in complex hydrocarbons and even water ice, a surprising discovery given the searing temperatures so close to the star. This suggests that the star that died was significantly more massive than our Sun, likely a star that began its life with several times the Sun's mass. Such stars forge a far greater diversity of elements in their nuclear furnaces, As it neared the end of its life, it underwent a series of dramatic pulsations, dredging up these newly synthesized elements from its deep interior and scattering them into space. The detection of these compounds turns the nebula into more than just a visual wonder. It becomes a floating chemical factory. The complex molecules and ices we detect are the very building blocks of life, being flung out into the interstellar medium, where they may one day become part of new planetary systems and perhaps the ingredients for biology elsewhere in the galaxy. The story of this nebula is still being written. Recent observations from the Hubble Space Telescope have revealed incredible detail within the wings, showing a complex network of knots, filaments, and bubbles. These are the scars of a violent and chaotic ejection process. The central star did not shed its atmosphere in one smooth, continuous flow, but in a series of fits and starts. Powerful, episodic outbursts sent shockwaves rippling through the already expanding gas, creating the intricate, clumpy structures we observe today. Furthermore, the central star itself remains shrouded in mystery. Despite its tremendous heat, it is incredibly faint at visible wavelengths, completely hidden by the very dust belt it helped to create. We only know of its extreme temperature and power indirectly, by studying the highly ionized gases in the nebula that can only be produced by such a searing ultraviolet source. The Butterfly Nebula, therefore, stands as a magnificent and ongoing puzzle. It is a testament to the chaotic and channeled nature of stellar death, a chemical reservoir seeding the galaxy with life's potential, and a stark reminder that even in its final moments, a star can create one of the most beautiful and complex structures in the entire cosmos. Leaving behind the vast, winged silhouette of the butterfly, we now encounter a celestial object so twisted and intricate it appears to be a galaxy within a galaxy. At number 14 on our list is NGC 5189. An object that so thoroughly defies the conventional appearance of a planetary nebula that for many years its true nature was a subject of debate. Through a telescope, it doesn't present a clean, elliptical or bipolar form. Instead, it unveils a spectacular S-shaped structure of glowing filaments, dense knots, and complex loops that looks astonishingly like a barred spiral galaxy, complete with a central bar and swirling arms spinning through the void. But this is a profound illusion of scale. We are not looking at a colossal system of billions of stars, but at the exquisitely detailed wreckage of a single, dying sun, a cosmic tapestry woven by one of the most dynamic gravitational dances in the universe. The secret to this unparalleled complexity lies in the heart of the nebula, where astronomers have discovered not one, but two stars locked in a close orbital embrace. This central binary system is the master architect of the entire spectacle. The primary star is the one that reached the end of its life, swelled into a red giant, and ultimately ejected its outer layers to create the nebula. But it did not do this in isolation. Its companion star orbits so closely that its gravity has profoundly influenced every aspect of the ejection process. As the dying star shed its atmosphere, the pull from the smaller companion star prevented the material from expanding away evenly. Instead, the gas was funneled into a dense central disk that we see as the bright bar, while also being channeled outward along specific pathways dictated by the star's orbital motion. The most crucial piece of this puzzle, however, is a phenomenon known as precession. Think of a spinning top as it begins to slow down. Its axis of rotation starts to wobble in a slow, conical motion. That is precession. In the case of NGC 5189, the entire binary system is thought to be undergoing just such a wobble. As the two stars orbit each other, their combined gravitational field acts like a giant, unstable gyroscope. This means that the direction from which the dying star ejects its fastest, most focused jets of material is not fixed. Over time, the axis of these jets slowly sweeps around the sky, tracing out a vast cone in space. Imagine holding a garden hose that is spraying a powerful jet of water, and then you slowly begin to rotate the nozzle. the stream of water would paint a spiral pattern on the ground. In the case of NGC 5189, the central star system is that rotating nozzle, and the jets of gas are painting a spiral pattern across the interstellar canvas, but on a scale that is truly astronomical. This precessing jet model elegantly explains the nebula's most striking feature, its apparent spiral arms. The glowing S-shaped filaments are not static structures, but are the fossilized tracks left behind by the wobbling jets. As the jet axis precessed over thousands of years, the high-speed material it ejected sequentially illuminated different parts of the surrounding, slower-moving gas cloud. Each sweep of the jet created a new, curved rim of shocked and glowing gas. The result is this layered, labyrinthine structure that we see today, a time-lapse photograph of a stellar jet's graceful, cosmic wobble. Observations from the Hubble Space Telescope provide stunning confirmation of this theory, revealing multiple distinct bubbles and arcs within the nebula that align perfectly with the idea of an outflow that has been constantly changing its direction. This makes NGC 5189 a unique historical record, allowing us to chart the precise precessional history of a binary star system over its final millennia. Beyond its breathtaking geometry, the nebula is also a vibrant chemical palette. Its gases glow in brilliant hues of red and green, indicating the presence of hydrogen and oxygen, but it also shows strong emission from nitrogen, suggesting the original star was fairly massive and successfully fused heavier elements in its core before its death. The central binary system remains active, with the hot white dwarf remnant pouring out ultraviolet radiation that keeps the entire intricate sculpture illuminated. The entire system serves as a stunning demonstration of how binary interactions are not just a minor footnote in stellar evolution, but can be the dominant force, turning a simple expanding shell into a work of unparalleled cosmic art. NGC 5189 challenges our very definitions, proving that from the death of a single star, a structure can emerge that rivals the grandest designs in the universe, all orchestrated by the slow, gravitational waltz of two stellar partners. While the death throes of individual stars create some of the cosmos's most intricate sculptures, we now turn our attention to entire galaxies where the core itself is a raging engine of almost unimaginable power. Our next three strange objects, NGC 253, NGC 1068, and NGC 4151, represent different facets of galactic hyperactivity, from explosive star formation to the terrifying gravitational influence of supermassive black holes. First, let's journey to the southern constellation of Sculptor and number 15 on our list, NGC 253, also known as the Sculptor Galaxy. Even through a small telescope, this galaxy is a spectacular sight, a nearly edge-on spiral that appears as a bright, silvery sliver of light, but its beautiful, serene appearance is deceptive. NGC 253 is one of the closest and brightest examples of a starburst galaxy, a system undergoing an extreme, galaxy-wide episode of star formation. Within its swirling arms, and especially in its central region, stars are being born at a rate that is truly ferocious, up to 10 times faster than in our own relatively quiet Milky Way. This isn't a gentle process, it is a violent, self-consuming firestorm of creation. The cause of this stellar frenzy is the galaxy's immense reservoirs of dense gas and dust. As these vast clouds collapse under their own gravity, they fragment into thousands of stellar nurseries, lighting up the galaxy's core with the brilliant blue light of massive, young, hot stars. These stars live fast and die young, exploding as supernova within only a few million years. These explosions, in turn, shock surrounding gas clouds, triggering further rounds of star formation in a relentless, self-perpetuating cycle. The entire central region of NGC 253 is a cacophony of birth and death, a place where the very interstellar medium is being violently churned and recycled. But such intense activity comes at a cost. The supernova and powerful stellar winds from the most massive stars are blowing a colossal galactic superwind, a fountain of hot gas and heavy elements that is being expelled from the galaxy's disk at high speeds. This wind, visible in X-ray and radio observations, is effectively limiting the galaxy's own growth, blowing away the very raw materials that fuel future star formation. NGC 253 offers us a front-row seat to a short-lived yet critically important phase in a galaxy's life. It shows us what happens when a galaxy taps its entire gas reservoir at once, a brilliant but unsustainable blaze of stellar glory that can dramatically shape its future evolution. It is a stark reminder that even on the scale of entire galaxies, periods of intense creativity are often inextricably linked with profound self-destruction. For an even more extreme and energetic type of galactic core, we look to our number 16, NGC 1068, better known as Messier 77 or M77. Located in the constellation Cetus, this is a spiral galaxy that appears to have a perfectly normal structure, with graceful arms winding around a bright, star-like nucleus. However, that brilliant core is the source of its strangeness. M77 is the prototypical example of a Seyfert galaxy, a class of spiral galaxies whose centers outshine the combined light of all their billions of stars. The power source for this incredible brilliance is not a cluster of supernova or a burst of star formation, but something far more concentrated and potent, a supermassive black hole. At the heart of M77 lies a black hole with a mass estimated to be around 15 million times that of our Sun. This gravitational monster is not dormant, it is actively feeding. Vast quantities of interstellar gas, dust, and even entire stars are spiraling down into an incredibly hot, bright, and rapidly rotating structure called an accretion disk that surrounds the black hole. The friction and tremendous gravitational forces within this disk heat the material to millions of degrees, causing it to glow with a blinding intensity across the entire electromagnetic spectrum, from radio waves to gamma rays. What makes M77 such a vital object for astronomers is that it presents a unique and revealing geometry. We are viewing this galaxy not quite face-on and not quite edge-on, but at an oblique angle. This perspective allows us to see the central powerhouse, but our view is partially obscured by a thick, donut-shaped ring of dust and molecular gas, known as a torus, that surrounds the accretion disk. This torus acts like a cosmic lampshade, hiding the very innermost region from our direct line of sight, while allowing the intense radiation to flood out along its poles, illuminating the surrounding gas clouds. These clouds, located hundreds of light years from the black hole, are fluorescing in response to the ultraviolet and X-ray radiation, much like the gas in a planetary nebula. By studying the light from these clouds, astronomers can probe the physics of the accretion process happening close to the event horizon, a region otherwise impossible to resolve. M77 is essentially a natural laboratory, giving us an unprecedented look at the complex structure and energetic output of an active galactic nucleus, a phenomenon that was utterly mysterious to astronomers just a few decades ago. This brings us to our 17th and perhaps most visually striking active galaxy, NGC 4151, which has earned the unforgettable nickname the Eye of Sauron for its hauntingly familiar appearance. Located in the constellation Canes Venatici, this galaxy presents a brilliant, star-like nucleus surrounded by a perfect, faint ring of reddish gas. The resemblance to the fictional Dark Lord's all-seeing eye is uncanny and deeply rooted in its real physical structure. The central pinprick of light is once again the signature of a voracious supermassive black hole, this one weighing in at around 50 million solar masses. The glowing red ring, however, is not a single structure but is actually composed of two distinct components seen in projection. There is an inner region of intense star formation, a starburst ring, and an outer ring of gas that is being illuminated and ionized by the fierce radiation from the active nucleus. This creates a multi-layered system where both black hole accretion and rampant star formation are happening simultaneously, a relatively rare and fascinating combination. NGC 4151 is particularly famous for its intense and variable X-ray emissions. The black hole's accretion disk is so turbulent and dynamic that it produces powerful flares in X-ray brightness, sometimes doubling in intensity over just a few hours. This rapid variability provides a crucial clue to the size of the emitting region, which must be incredibly compact, no larger than our own solar system, to change so quickly. This galaxy has been the subject of extensive multi-wavelength campaigns, with observatories like the Chandra X-ray Observatory and the Hubble Space Telescope working in concert to unravel its secrets. They have mapped outflows of gas and detected evidence for a warped accretion disk, possibly caused by the gravitational influence of a second, smaller black hole in a binary system. The Eye of Sauron is not a static, malevolent entity, but a dynamic and complex physical system where gravity, radiation, and magnetic fields are locked in a violent struggle for dominance. It serves as a stunning example of how the most energetic and mysterious phenomena in the universe can manifest in forms that are both scientifically profound and culturally resonant, a perfect blend of cosmic terror and beauty. Penetrating deep into intergalactic space, we arrive at a galaxy that serves as the beating, turbulent heart of one of the most massive structures in the known universe. At number 18 on our list is NGC 1275, the dominant central galaxy of the immense Perseus cluster, a gathering of thousands of galaxies located about 230 million light-years away. This is not a serene island universe. It is a cosmic predator, a galaxy that has grown to gargantuan proportions by cannibalizing its smaller neighbors, and it sits at the center of a superheated atmospheric ocean. The space between the galaxies in the Perseus cluster is not empty. It is filled with a searing plasma known as the intracluster medium, with temperatures soaring to tens of millions of degrees. In this environment, you would expect any delicate, cold structures to be vaporized instantly. Yet, that is precisely what makes NGC 1275 so profoundly strange. From its core, a spectacular, ghostly network of dark, filamentary structures erupts, stretching for tens of thousands of light-years into the surrounding inferno like cosmic seaweed rooted in a hydrothermal vent. These are not stars, they are colossal threads of cold molecular gas, a shocking and seemingly impossible presence within a furnace hot enough to tear molecules apart. The existence of these filaments presents a monumental physics puzzle. How can these delicate, relatively cold strands, with temperatures hovering just tens of degrees above absolute zero, survive for millions of years while immersed in a plasma that is over 50 million degrees hot? Simple thermodynamics dictates that the hot intracluster medium should heat the cold gas, causing it to dissipate and evaporate in a cosmic instant. The fact that it does not mean some powerful force is actively protecting and sustaining these structures. Astronomers believe the answer lies in a combination of magnetic fields and an ongoing dynamic process. Observations from telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory have been crucial here. The leading theory suggests that as the supermassive black hole at the galaxy's core undergoes its feeding cycles, it doesn't just produce radiation. It also generates powerful outbursts in the form of buoyant bubbles of relativistic plasma. These bubbles rise through the intracluster medium, pushing the hot gas aside and creating a complex, stirring motion. Within this churning environment, magnetic fields permeating the entire cluster are thought to act like a skeletal framework. As the cold gas from the galaxy's core is pulled out, perhaps by the buoyant bubbles or by gravitational interactions, these magnetic fields provide a supporting scaffold. They wrap around the cold gas filaments, insulating them from the surrounding heat and preventing them from being destroyed by thermal conduction. It's analogous to how a layer of air trapped in a wetsuit protects a deep sea diver from the freezing ocean water. The magnetic fields create a protective barrier that allows the cold gas to persist in a state that should be utterly lethal. This intricate balance between the black hole's explosive feedback and the protective embrace of magnetism is what allows these magnificent structures to form and endure. They are a visible manifestation of the complex energy cycle that governs the life of galaxy clusters, a cycle where a monstrous black hole's violent outbursts ironically create the conditions necessary for the preservation of delicate cold gas. Without this feedback, the central galaxy would likely have long ago exhausted its cold gas reservoir and ceased forming stars. Instead, the black hole's own energy is recycling material in a self-regulating loop. The significance of these filaments extends far beyond their striking appearance. They are more than just a cosmic curiosity. They are a direct pipeline of raw material for future star formation. The cold molecular gas within them is the very stuff from which new stars and planetary systems are born. In the hostile environment at the center of a galaxy cluster, this gas should not exist, and yet here it is, being funneled from the galactic core out into the halo and then likely falling back in. This process provides a continuous supply of fuel, potentially explaining why these giant central galaxies, known as brightest cluster galaxies, can remain active and form stars long after their more isolated counterparts have settled into a quiet old age. The filaments of NGC 1275 are therefore a key to understanding the longevity and evolution of the most massive galaxies in the universe. They show us that these galaxies are not passive entities, but are dynamic systems engaged in a complex gravitational and electromagnetic dance with their environment, a dance where destruction and creation are two sides of the same coin. Now we move from the giant central galaxies of clusters to one of the most contentious and philosophically charged pairings ever observed in the heavens. At number 19 on our list, we find the seemingly innocent duo of NGC 4319 and Markarian 205. To the eye, the arrangement is striking and suggestive. NGC 4319 is a classic barred spiral galaxy floating in the void of the constellation Draco, and seemingly attached to it by a faint, luminous bridge of matter is a brilliant, star-like point known as Markarian 205. This visual connection strongly implies a physical relationship, a cosmic umbilical cord suggesting the two objects are neighbors, gravitationally bound and interacting. This interpretation, however, catapulted this pair into the center of a firestorm in modern cosmology, a debate that challenged fundamental assumptions about the scale and nature of the universe itself. The root of the controversy lies in a single, crucial measurement, redshift. In the early 20th century, astronomer Edwin Hubble made the landmark discovery that the light from distant galaxies is shifted toward the red end of the spectrum, and that this redshift generally increases with distance. The prevailing explanation, which forms the bedrock of modern cosmology, is that this redshift is a Doppler effect caused by the expansion of the universe itself. As space stretches, it stretches the wavelength of light traveling through it, making it redder. Therefore, a greater redshift indicates a greater distance and a higher velocity of recession. When astronomers measured the redshifts of these two objects, they got a shocking result. The galaxy NGC 4319 has a modest redshift, placing it at a comfortable distance of about 80 million light-years away. The quasar Markarian 205, however, has a redshift more than 10 times greater, which, according to the standard interpretation, would mean it is billions of light-years away, far in the background. The luminous bridge between them, if real, would then be an impossible structure, a physical connection stretching across an unthinkable void and defying the laws of physics. This paradox made NGC 4319 and Markarian 205 a central battleground in the once heated redshift debate. A minority of astronomers, most notably Holt and Arp, used pairs like this to argue that redshift was not a reliable measure of distance. Arp proposed that quasars were not incredibly distant objects, but were instead being ejected from the cores of active nearby galaxies like NGC 4319. In this radical view, their high redshifts were an intrinsic property, perhaps due to extreme youth or some new physics, not cosmic expansion. The luminous bridge was his prime evidence, proof that the two were physically linked despite what their redshift said. For proponents of this theory, this pair was a direct challenge to the Big Bang model, suggesting the universe was not uniformly expanding and that our understanding of its most basic rules was flawed. The mainstream astronomical community, however, was deeply skeptical. The implications of throwing out the cosmological redshift were immense, unraveling decades of work on the scale, age, and evolution of the universe. The counter-argument was that the bridge was an illusion, a trick of light and chance alignment. Perhaps it was a faint foreground structure within NGC 4319 itself, or a random, unrelated wisp of gas that just happened to line up perfectly with the distant quasar from our vantage point. The debate raged for years, fought in scientific journals and at conferences, with this unassuming pair of celestial points serving as the proxy for a much larger war over cosmological principles. The matter was finally put to rest with the unparalleled resolving power of the Hubble Space Telescope. Its crisp images revealed the situation with stunning clarity. The controversial bridge of light was indeed an illusion. What appeared as a continuous connection in ground-based telescopes was resolved into a complex mix of overlapping features. Some of the perceived structure was due to internal dust lanes and faint spiral arms within the galaxy itself, while other parts were attributed to subtle optical effects and the limitations of earlier photographic plates. The final nail in the coffin came from spectroscopic analysis, which showed no evidence that the material in the galaxy and the light from the quasar were physically interacting. They were simply occupying the same line of sight, a magnificent cosmic coincidence. Markarian 205 was indeed a distant quasar, a beacon from the early universe shining billions of light years behind the foreground galaxy. Yet, the legacy of this controversial pair is far from insignificant. The intense scrutiny they received drove significant advancements in observational technology and data analysis techniques. The debate forced astronomers to be more rigorous in distinguishing between physical associations and simple alignments, a critical skill in a crowded universe. While Arp's specific hypothesis was disproven, his work highlighted the importance of being vigilant for genuine anomalies that could challenge our models. NGC 4319 and Markarian 205 stand as a permanent monument to the scientific process itself, a reminder that even beautiful and compelling ideas must ultimately bow to the unforgiving court of empirical evidence. They teach us that the universe is full of apparent mysteries that, upon closer inspection, reinforce the very laws we use to understand it, while always leaving the door open for the next genuine paradox that might just change everything. If the Perseus cluster represents a complex dance of feedback and preservation, then our next object showcases the raw, unbridled power of a supermassive black hole operating at its most extreme. At number 20 on our list is the colossal elliptical galaxy NGC 4486, universally known as Messier 87 or M87. This isn't just any galaxy, it is a Titan, a dominant member of the nearby Virgo cluster, containing trillions of stars and weighing in at nearly 2,000 times the mass of our own Milky Way. For decades, M87 has been a celebrity among astronomers, but not for its vast population of ancient stars. Instead, all attention is drawn to a seemingly insignificant point at its very core, and to a brilliant blue-white spear of light that erupts from it, stretching an almost incomprehensible 5,000 light-years out into the blackness of intergalactic space. This is M87's legendary jet, a cosmic searchlight signaling the presence of one of the most formidable engines in the local universe. The power source for this phenomenal jet is, of course, the supermassive black hole at the galaxy's heart. But this is no ordinary black hole. The one residing in M87 is a true behemoth with a mass measured at a staggering 6.5 billion times that of our Sun. To grasp that scale, imagine an object so massive that its event horizon, the point of no return, would easily engulf our entire solar system out beyond the orbit of Pluto. This gravitational monster is not sleeping. It is an active and voracious engine. As immense quantities of interstellar gas, dust, and even entire stars are drawn in by its overwhelming gravity, this material does not fall straight in. Instead, it spirals down into a rapidly rotating, superheated structure called an accretion disk, which glows fiercely across the entire electromagnetic spectrum from the friction of countless particles rubbing against one another at near light speed. It is from this maelstrom that the jet is born. The incredible rotational energy and powerful magnetic fields generated by the accretion disk act like a colossal particle accelerator. They funnel some of the infalling material away from the poles of the black hole, accelerating it into two oppositely directed beams of magnetized plasma. The physics of this process is among the most extreme in all of cosmology. The particles in this jet are accelerated to over 99% the speed of light, making it a relativistic jet. The jet we see so prominently is the one pointing almost directly at us, its brilliance amplified by relativistic effects. Its distinctive blue color comes from a phenomenon known as synchrotron radiation, emitted by electrons spiraling at fantastic velocities along the jet's powerful magnetic field lines. This entire structure is a continuous, high-energy explosion that has been ongoing for millions of years, a testament to the vast reserves of fuel available to a black hole at the center of a galactic giant. The historic significance of M87's black hole cannot be overstated. In April 2019, the world witnessed a scientific milestone decades in the making. The Event Horizon Telescope Collaboration, a global network of radio telescopes working in unison, released the first ever direct image of a black hole's shadow. And the subject of that first, blurry, orange-ringed portrait was none other than the supermassive black hole at the core of M87. That image was not of the black hole itself, no light can escape from it, but of its silhouette against the brilliant backdrop of its own accretion disk. This provided the most direct visual evidence possible for the existence of these cosmic predators, and confirmed that the theoretical predictions about their behavior in such an extreme environment were astonishingly accurate. It transformed this distant galaxy from an object of study into an icon, a place where humanity first directly glimpsed the edge of the known physical world. Beyond its famous jet and its photographed shadow, M87 serves as a critical laboratory for understanding how supermassive black holes shape their entire galactic environment. The energy output from the black hole's accretion process and its jet is so immense that it regulates the formation of new stars throughout the galaxy. The heat and powerful winds it generates prevent the vast reservoirs of cool gas in M87 from collapsing to form new stars, effectively keeping this giant elliptical galaxy red and dead, dominated by older, redder stars. This process, known as AGN feedback, is a key piece in the puzzle of galactic evolution, explaining why the most massive galaxies in the universe are no longer bustling stellar nurseries. The mighty jet, visible across intergalactic space, is thus more than just a spectacular light show. It is the visible signature of a central governor, a cosmic thermostat that controls the life cycle of an entire galaxy, demonstrating that even the largest structures in the cosmos are held in balance by the most extreme objects within them. Leaving behind the serene giants and active hearts of single galaxies, we plunge headlong into a celestial event of almost biblical proportions, the spectacular and violent merger of two entire star systems. At numbers 21 and 22 on our list, we find the utterly captivating duo of NGC 4038 and NGC 4039, known collectively across the universe as the antennae galaxies. From the moment you see an image of this system, the name makes perfect sense. Two galaxies locked in a gravitational embrace have been stretched and distorted, flinging out two vast, sweeping arcs of stars, gas, and dust that stream into intergalactic space like the delicate antennae of some colossal cosmic insect. These tidal tails are the unmistakable signature of a galactic collision in progress, a fleeting and brilliant phase in the life of galaxies that forever alters their destiny. The story of the antennae began hundreds of millions of years ago. Astronomers believe these two galaxies, which were likely originally separate spiral galaxies not unlike our own Milky Way and the Andromeda Galaxy, began their fateful dance around that time. As they made their first close pass, their mutual gravity acted like a tremendous tidal force, far more powerful than the pull that our moon exerts on Earth's oceans. This force did not simply pull the galaxies together, it ripped them apart. Stars, which are so far apart that they almost never collide, were flung from their original orbits, while the vast clouds of gas and dust within the galaxies were compressed, shocked, and drawn out into those spectacular long streams. The name tidal tails is wonderfully descriptive, as they are the cosmic equivalent of the tidal bulge raised in Earth's oceans, but on a scale of hundreds of thousands of light years and frozen in time for hundreds of millions of years. But the most dramatic and transformative events are happening not in the long, elegant tails, but in the violently churning core of the merger. This is where the true cosmic fireworks are on display. The collision has triggered an extreme, galaxy-wide starburst, a firestorm of star formation of almost unimaginable intensity. Within the overlapping central regions, vast clouds of interstellar gas compressed by the gravitational chaos have fragmented and collapsed all at once, igniting the birth of millions of new stars. This isn't the relatively orderly star formation we see in isolated spiral arms. This is a frantic, almost desperate burst of creation. The most prominent of these newborn stars are the brilliant blue supergiants, massive, hot, and short-lived stars that flood the region with intense ultraviolet light, causing any remaining hydrogen gas to glow with a characteristic pinkish-red hue. Sprinkled throughout this maelstrom are over 1,000 brilliant young globular clusters, appearing as tiny, sparkling knots of light. These are the true future legacy of this collision. Each one is a dense ball containing hundreds of thousands or even millions of stars, all born from the same colossal gas cloud. In a stable galaxy like our own, globular clusters are ancient relics over 12 billion years old. Here, in the antennae, we are witnessing the formation of entirely new globular clusters, something that has not happened in the Milky Way for eons. The life cycle within this stellar nursery is both creative and destructively fast. The most massive of these newborn stars burn through their nuclear fuel in only a few million years, a cosmic blink of an eye, and end their lives in titanic supernova explosions. These blasts send shockwaves rolling through the surrounding gas, simultaneously scattering newly forged heavy elements like oxygen, silicon, and iron back into the interstellar medium, while also triggering the collapse of nearby gas clouds to form yet another generation of stars. The environment is a continuous, self-regulating cycle of death and rebirth, seeding the future galaxy with the complex chemistry necessary for planets and potentially life. This ferocious pace cannot last forever, however. The very starburst that defines the antennae is also consuming its fuel source at a prodigious rate. Within a few hundred million years, most of the available gas will have been either turned into stars or blown away by the relentless stellar winds and supernova explosions, effectively quenching further star formation. As for the ultimate fate of this system, the future is both clear and spectacular. The two galactic cores, each harboring its own supermassive black hole, are currently separated but will continue to spiral inward over the next several 100 million years. Dragged by dynamical friction against the background of stars and dark matter, they will eventually merge into a single, even more massive black hole, an event that will ripple the fabric of space-time with gravitational waves. Once the dust literally settles, the violent, disorganized structure we see today will be gone. In its place will stand a single, large elliptical galaxy, a smooth, featureless collection of older stars, a quiet retirement for a system that once hosted one of the most energetic events in the universe. The long, graceful tidal tails will slowly dissipate, their stars either falling back into the new galaxy or becoming part of the lonely intergalactic population. The antennae galaxies offer us a stunningly detailed preview of the fate that awaits our own Milky Way when it collides with the Andromeda galaxy in about 4 billion years. They are a living laboratory, showing us that the universe is not a static collection of islands, but a dynamic, evolving web where colossal, transformative collisions are not the exception, but a fundamental rule of cosmic evolution. But if the antennae galaxies show us the creative violence of galactic collisions, our next object reveals a more intimate and equally beautiful kind of destruction, that of a single star ending its life in a cataclysm so powerful its echo is still visible millennia later. At number 23, we encounter not one, but two entries in the NGC catalogue that are part of a single, magnificent whole: NGC 6960 and NGC 6992, two brilliant sections of the sprawling Veil Nebula. Located in the constellation Cygnus, the Veil is one of the most spectacular and photogenic objects in the entire night sky, a ghostly tapestry of glowing filaments that stretches across an area 6 times larger than the full moon. To the eye, it looks like delicate, luminous lacework, a wispy and ethereal cloud drifting silently in the void. But this serene beauty is a glorious lie. What we are actually witnessing is the expanding blast wave from a supernova explosion, a stellar detonation so violent that it would have outshone the entire galaxy for a brief, terrifying moment, and whose remnant still races outward at hundreds of kilometers per second. The story of the Veil Nebula began not thousands, but roughly 10,000 years ago, when a star vastly more massive than our Sun reached the end of its life. Having exhausted the nuclear fuel in its core, it could no longer support its own immense weight against the crush of gravity. In a fraction of a second, its core collapsed, triggering a titanic rebound explosion that blasted the star's entire outer envelope into space at a significant fraction of the speed of light. The energy released in that single event is almost beyond human comprehension. For a few weeks, that one star shone with the brilliance of billions of suns. The flash of light has long since traveled onward across the galaxy, but the physical remnant of that explosion, the expanding sphere of stellar debris, is what we see today as the Veil Nebula. The entire structure is now over 110 light-years across and continues to grow, a testament to the sheer power of the initial blast. The key to understanding the nebula's breathtaking filamentary structure lies in the physics of shock waves. The initial supernova explosion sent a spherical shock front, a wall of highly compressed, superheated gas and energy ramming into the surrounding interstellar medium at hypersonic speeds. As this shock wave plows through space, it doesn't move smoothly. It encounters regions of slightly denser gas, and as it passes over them, it creates complex turbulence, much like a wave breaking over rocks on a shoreline. The glowing filaments we see so clearly in photographs from the Hubble Space Telescope are essentially the edges of these vast, rippled shock fronts. The gas within them is being heated to millions of degrees by the passage of the shock, causing it to glow fiercely. Different chemical elements within the debris glow with different colors. The vivid red hues come from ionized hydrogen, while the striking blue-green colors are emitted by doubly ionized oxygen atoms. This intricate, tangled appearance is not a sign of chaos, but a frozen record of the incredibly complex interaction between the expanding shock wave and the pre-existing landscape of the interstellar medium. Our two specific NGC objects, 6960 and 6992, represent two of the brightest and most defined arcs in this cosmic bubble. NGC 6960 is also famously known as the Witch's Broom Nebula, a long, delicate sweep of filaments that forms the western portion of the veil. It is particularly notable for the bright star 52 Cygni, which appears to be embedded in the nebula but is actually a foreground star that just happens to lie along our line of sight, providing a brilliant and convenient guidepost for amateur astronomers. On the opposite eastern side of the loop lies NGC 6992, a much broader and more complex network of filaments that often earns the name Pickering's Triangle, after the Harvard College Observatory director who first noted its photographic presence. This section reveals the full, intricate detail of the shock structure, with countless intertwined threads and delicate loops that look like a cosmic spiderweb. Observing these two sections through a telescope with an oxygen 3 filter is a transformative experience, as the faint, glowing tendrils seem to materialize out of the darkness, revealing the sheer scale and delicate violence of this ancient explosion. Studying the Veil Nebula is like conducting an archaeological dig into a star's corpse. By carefully measuring the expansion rate of the filaments and comparing it to the nebula's current size, astronomers can effectively rewind the clock, confirming that the explosion did indeed occur around 10,000 years ago. Furthermore, the chemical composition of the glowing gas serves as a direct sample of the star's interior. The strong emission from oxygen, sulfur, and other heavy elements tells us that the progenitor star was a true cosmic forge, creating these elements through nuclear fusion during its life and then seeding them back into space in its death throes. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all created in stars like this one and scattered across the galaxy by supernova explosions exactly like the one that created the Veil. This magnificent remnant is therefore far more than a pretty picture. It is a vital recycling plant for the galaxy, a source of the heavy elements necessary for planets, oceans, and life itself. It is a permanent monument to the fact that from the most violent endings come the essential ingredients for new beginnings. Now we shift our gaze from the ancient, fading echoes of a supernova to a seething cauldron of stellar birth, a place where the universe is forging new suns on a truly epic scale. At number 24 on our list, we encounter NGC 6357, the magnificent Lobster Nebula. Located in the tail of the constellation Scorpius, this is not a quiet, glowing cloud. It is a sprawling, turbulent stellar nursery, a cosmic factory operating at maximum capacity. From a distance, its complex structure of glowing gas and dark, obscuring dust does somewhat resemble the form of a lobster, with bright claws and a segmented body, all sculpted by the ferocious output of the colossal stars being born within it. But this captivating shape is merely the backdrop for the true heart of the mystery, a star cluster so extreme that it initially challenged our fundamental understanding of how massive a star can possibly become. At the very core of this nebula lies the open cluster Pisces 24, a dense gathering of stellar titans. When this cluster was first studied, one star in particular, known as Pisces 24-1, stood out as a point of light so brilliant that astronomers calculated it must be a single, monstrous star with a mass estimated at an almost unbelievable 200 to 300 times that of our Sun. This presented a monumental problem. According to established astrophysical models, there is a theoretical upper limit to stellar mass, thought to be around 150 solar masses. Beyond this limit, the internal radiation pressure from a star's own nuclear fusion becomes so intense that it would literally blow the star apart, preventing it from accumulating or holding onto any more material. Pisces 24-1 appeared to be a flagrant violator of this cosmic speed limit, an impossible star that threatened to rewrite the textbooks. The mystery was only resolved with the unparalleled sharp vision of the Hubble Space Telescope. Hubble's high-resolution images revealed the truth in stunning detail. Pisces 24-1 was not one single, impossibly massive star at all. It is, in fact, a tight-knit multiple star system, a miniature constellation in its own right. Hubble showed at least 3, and possibly more, brilliant component stars orbiting each other in a tight gravitational dance. What appeared as a single point of light from the ground was actually the combined brilliance of several individual supergiant stars, each one spectacularly massive in its own right, but each comfortably within the accepted physical limits. This discovery was a perfect example of a cosmic illusion, where the limitations of our observation can create apparent paradoxes that are only resolved by peering closer. Each of these stars is still a behemoth, weighing in at around 100 solar masses, and they are among the most luminous objects in our entire galaxy, each shining with the brightness of nearly 1 million suns. The presence of such stellar powerhouses has a profound and violent effect on their surroundings. The intense ultraviolet radiation blasting from the stars of Pisces 24 is relentlessly eroding the very nebula that gave them birth. This radiation is so energetic that it strips electrons away from the atoms in the surrounding hydrogen gas, causing it to glow with the characteristic red hue of an emission nebula. But the process doesn't stop there. The fierce stellar winds flowing from these massive stars, carrying immense amounts of material away at millions of miles per hour, are carving out vast cavities and sculpting the intricate pillars and dark lanes of dust we see throughout the Lobster Nebula. In some regions, these winds are compressing the surrounding gas, triggering the collapse of new clouds and initiating the birth of the next generation of stars, a process known as triggered star formation. In other areas, they are outright destroying potential stellar nurseries, blowing the raw material away into interstellar space. The entire nebula is a dynamic battlefield, a continuous cycle of creation and destruction orchestrated by its most powerful and short-lived residents. Adding to the nebula's dramatic appearance are the towering columns of gas and dust, reminiscent of the famous pillars of creation in the Eagle Nebula. These structures, known as elephant trunks, are the densest, most resilient parts of the cloud, stubbornly resisting the intense erosion from the central cluster. They act as cosmic incubators, shielding dense cores of gas within their shadows where new stars are currently in the process of formation. Even as the outer layers of these pillars are being boiled away by the stellar radiation, the protected cores may be collapsing to form new solar systems, a stark illustration of how stellar death and birth are often two sides of the same coin. The Lobster Nebula, therefore, offers us a holistic view of the stellar life cycle. Within its bounds, we see the raw material, the ongoing process of violent birth, the mature, brilliant stars in their prime, and the eventual fate of those same stars, which will one day explode as supernova, just like the one that created the Veil Nebula, seeding the galaxy with heavy elements and triggering yet another round of cosmic creation. It is a place of both immense beauty and terrifying power, a constant reminder that our galaxy is a living, breathing, and ever-changing entity. But if the Lobster Nebula is an epic of stellar birth, our next destination is a theater of stellar death on a scale so grand it defies belief. At number 25 on our list of strange objects, we arrive at NGC 3372, the colossal Eta Carinii Nebula, also known as the Great Nebula in Carina. This is not merely a nebula, it is one of the largest and brightest stellar nurseries in our entire galaxy. A sprawling complex of glowing gas, dark dust lanes, and brilliant star clusters that would be a celebrated deep sky object in its own right. Yet, all of this cosmic splendor is overshadowed by the mesmerizing and terrifying drama unfolding at its very heart. The presence of the unstable, hypergiant star system known as Eta Carinii itself. This star is a cosmic time bomb, a celestial entity so volatile and unpredictable that its past eruptions have reshaped its surroundings, and its future holds the promise of one of the most energetic explosions the Milky Way has ever witnessed. The story of Eta Carinae's modern intrigue begins in the 19th century. For most of recorded history, it was a fairly unremarkable star, but around the year 1843, it underwent a cataclysmic event that stunned astronomers worldwide. In what is now known as the Great Eruption, Eta Carinae suddenly became the second brightest star in the entire night sky, outshone only by Sirius despite its vast distance of 7,500 light-years. For a decade, it blazed with an intensity that rivaled the light of entire nebulas, a display of raw stellar power that was completely unprecedented. Then, just as mysteriously, it began to fade, eventually dropping below naked eye visibility. We now understand that the star did not explode in a supernova. Instead, it underwent a colossal, non-terminal eruption. The star ejected an immense amount of its own mass, at least 10 times the mass of our entire Sun, in a single, violent paroxysm. This material was blown into space at speeds of millions of miles per hour, but not fast enough to escape the star's tremendous gravity completely. Instead, it formed a dense, expanding cloud that enshrouded the star, causing its dramatic fade from view as the dust blocked its brilliant light. The direct result of that 19th century explosion is the stunning structure we see today, known as the Homunculus Nebula. The name means little man, and through powerful telescopes like Hubble, it does appear as a bizarre, dumbbell-shaped cloud, a bipolar nebula with two opposing lobes of gas and dust. This is not a peaceful, expanding shell. It is a dynamic and evolving structure, a fossilized record of that single, violent event. The lobes are expanding outward, and by measuring their motion, astronomers have been able to trace them back in time, confirming that they indeed originated from the Great Eruption of the 1840s. The homunculus is not a smooth cloud. Its surface is rippled with complex knots, ridges, and streaks, suggesting the ejection was incredibly turbulent and possibly shaped by a powerful magnetic field or the gravitational influence of a companion star. What makes it truly extraordinary is that we are witnessing this structure evolve in a human timescale. Observations separated by just a few years show clear changes in the nebula's fine details, offering a real-time laboratory for studying the aftermath of a stellar outburst of almost unimaginable magnitude. So, what could cause a star to behave in such an extreme manner? The prevailing model paints a picture of a binary system locked in a deadly dance. Eta Carinae is not one star but two. The primary is a luminous blue variable star, an incredibly massive and unstable hypergiant with a mass estimated at between 100 and 200 times that of our Sun. It is so massive that it is teetering on the very brink of stability, its own immense radiation pressure fighting a constant battle against the crushing force of its own gravity. It is believed that in the period leading up to the Great Eruption, the star approached its Eddington limit, the point where the outward push of its radiation perfectly balances the inward pull of gravity. This made its outer layers incredibly unstable, like a pot of water boiling over. The presence of a smaller, hotter companion star, which orbits the primary every 5.5 years in a highly elliptical path, adds a critical element of chaos. During their close approaches, the companion star likely plunges deep into the primary's extended, tenuous atmosphere, creating immense tidal forces and triggering massive instabilities that may have been the final catalyst for the Great Eruption. This binary interaction is the key to understanding the system's violent past and its uncertain future, and that future is the source of both scientific fascination and sober reflection. Eta Carinae is living on borrowed time. A star of such tremendous mass has a life expectancy of only a few million years, a mere blink in cosmic terms. It has already consumed the hydrogen in its core and is now fusing heavier elements in a desperate race against gravity. Its fate is almost certainly a core collapse supernova, and it may be just thousands of years away from this final cataclysm, or perhaps even much sooner. When it does go, it will not be a typical supernova. Given its enormous mass, it is a prime candidate for a hypernova, a supernova of exceptional energy that will be accompanied by a long-duration gamma-ray burst, one of the most luminous electromagnetic events known in the universe. For a brief time, it would shine with a brilliance comparable to the full moon, visible even in broad daylight. While situated at a safe distance that poses no threat to life on Earth, the event would be a spectacular celestial show and an unparalleled opportunity for astrophysics, allowing us to study the death of a true stellar monster and the creation of elements in real time. The Eta Carinae system, with its dramatic history and its ominous future, serves as a constant reminder that the universe is a place of both magnificent beauty and terrifying, raw power, where the life cycles of the largest stars are played out on a stage of truly epic proportions. While the dramatic, unstable giant Eta Carinae represents a star in its final, volatile chapter, our journey now takes us to the opposite end of the stellar life cycle, to places where stars are just beginning their brilliant lives. At numbers 26 and 27 on our list, we encounter two spectacular young open clusters, NGC 6231 and NGC 6383. These are not the ancient, tightly packed globular clusters that orbit the galactic halo. These are stellar nurseries, vibrant and fleeting gatherings of newborn stars that have just recently ignited their nuclear furnaces and are still often embedded within the glowing clouds of gas from which they formed. They offer us a pristine look at the earliest moments of a star's existence, a time of intense radiation and powerful winds that shape the very fabric of their cosmic surroundings. Our first target, NGC 6231, is nothing short of a stellar powerhouse. Located in the tail of the constellation Scorpius, this cluster is so bright and concentrated that it is easily visible to the naked eye as a fuzzy patch of light. But through a telescope, it resolves into a breathtaking collection of brilliant, hot, blue-white stars, a dazzling jewel box set against the Milky Way. This cluster is far more than just a pretty grouping. It is the central core of a much larger, sprawling stellar association known as Scorpius OB1. The term OB association refers to a loose grouping of massive, short-lived stars of spectral types O and B, the true giants and supergiants of the stellar world. These are the stars that live fast and die young, and their collective presence has a transformative effect on their environment. The sheer concentration of stellar might within NGC 6231 is staggering. The cluster contains dozens of these colossal stars, each one shining with the luminosity of tens or even hundreds of thousands of suns. Their combined ultraviolet output is so intense that it acts like a cosmic blowtorch, ionizing the vast surrounding clouds of hydrogen gas and creating a gigantic emission nebula that, while often too faint to see in amateur telescopes, is a prominent feature in astrophotos. This nebulosity is the lingering ghost of the original molecular cloud that gave birth to the cluster itself. The fierce stellar winds from these massive stars are simultaneously sculpting and eroding this cloud, blowing enormous bubbles and cavities in the interstellar medium. In some regions, this process is triggering the collapse of nearby gas clouds to form a second generation of stars, while in others, it is outright destroying potential stellar nurseries. NGC 6231 is therefore a dynamic and violent ecosystem, a place where the first generation of stars is actively and destructively shaping the conditions for the next. Studying this cluster and its extended association allows astronomers to understand the feedback loops that govern star formation rates across entire swaths of a galaxy, demonstrating how the birth of the largest stars can both promote and ultimately quench the birth of their smaller siblings. Just a short cosmic distance away, we find our 27th strange object, NGC 6383, At first glance, this cluster appears similar to its neighbor, a sparkling collection of young stars. However, it possesses a distinct personality and a fascinating central mystery. The entire cluster is dominated by one overwhelmingly brilliant star system, which immediately draws the eye. This is not a single star, but a complex and massive triple star system known as HD 159378. The primary component of this system is a brilliant O-type giant, a star so hot and massive that its own fate is almost certainly a core collapse supernova. The gravitational dance of this triple system is a key area of interest, as such close, massive companions can significantly influence each other's evolution through mass transfer and tidal forces. What makes NGC 6383 particularly intriguing for observers is the delicate nebulosity that surrounds it. Unlike the vast, faint emission structures around NGC 6231, the nebula associated with this cluster is a subtle reflection nebula. This means it does not glow with its own light from ionized gas, but instead shines by reflecting the brilliant blue-white light of its dominant central stars, much like a street lamp illuminating a faint mist. This ethereal glow, often catalogued as IC4665, is most visible in long-exposure photographs, where it appears as a wispy blue veil draped across the cluster. The presence of a reflection nebula, rather than an emission nebula, tells astronomers a great deal about the cluster's environment. It suggests that the most intense phase of ultraviolet radiation, the kind needed to ionize hydrogen, has already passed, perhaps because the densest gas has been blown away or the most short-lived, extreme O stars have already exploded. The surviving dust grains now simply scatter the starlight, creating a scene of comparative serenity compared to the violent ionization fronts of Scorpius OB1. When we consider these two clusters together, they provide a beautiful comparative lesson in stellar youth. NGC 6231 shows us the raw, unbridled power of a massive star cluster at its peak, actively tearing apart its natal cloud and flooding space with ionizing radiation. NGC 6383, by contrast, offers a glimpse into a slightly more evolved stage where the initial frenzy has subsided, leaving behind a brilliant multiple star system to illuminate the remaining dust in a more gentle, reflective glow. Both are young by astronomical standards, only a few million years old, but they highlight different moments in the early life of a star cluster. They remind us that star formation is not a single event, but a complex sequence of collapse, ignition, and feedback, where the most massive stars are the undeniable architects of their own environment, capable of both brilliant creation and swift, decisive destruction. Leaving behind the brilliant stellar nurseries of Scorpius, we venture into the constellation Cassiopeia, where a cosmic character from the early days of video gaming seems to have taken up residence among the stars. At number 28 on our list is NGC 281, universally nicknamed the Pac-Man Nebula. The moment you see a deep image of this object, the reason becomes delightfully obvious. This bright, roughly circular emission nebula is dramatically bisected by a thick, dark lane of obscuring dust that cuts across its southern portion, creating a perfect, gaping mouth. Combined with the nebula's round shape, the resemblance to the classic dot-chomping arcade icon is both uncanny and unforgettable. But this is far more than a simple cosmic coincidence. It is a vivid snapshot of the intense physical processes that govern the life cycles of giant molecular clouds. The iconic shape of the Pac-Man is a direct result of a dynamic interplay between light and shadow. The entire nebula is a vast cloud of primarily hydrogen gas, heated to a brilliant red glow by the torrent of ultraviolet radiation streaming from the immensely hot young stars at its core. The dark mouth, however, is not a void. It is an incredibly dense and cold region of gas and dust, a part of the original molecular cloud that has not yet been evaporated or blown away by the stellar winds. This dark lane is so thick that it completely blocks the brilliant emission from the glowing gas behind it, creating the striking silhouette that defines the nebula's personality. The intricate, clumpy structure within this dark dust, which gives the mouth its pixelated, almost digital appearance, reveals the turbulent, lumpy nature of the interstellar medium from which stars are born. We are essentially witnessing a cosmic silhouette, a shadow play on a scale of dozens of light years, where dark, cold material is being slowly eroded by the relentless light of newborn suns. The engine driving this entire spectacle is the young, energetic open cluster embedded deep within the nebula's heart, known as IC 1590. This compact group of stars is the very reason the Pacman Nebula exists in its current glowing form. The most massive members of this cluster are spectacular O-type and B-type stars, stellar behemoths that live fast and die young. Their surface temperatures are so extreme that they emit the majority of their energy in the ultraviolet part of the spectrum. This intense UV radiation is the power source that ionizes the surrounding hydrogen gas. The process is relentless. High-energy UV photons strike neutral hydrogen atoms, violently stripping away their electrons. When these electrons eventually recombine with protons, they release energy in the form of the characteristic red light that makes emission nebulae like this one so visually stunning. Without the fierce energy output of IC 1590, NGC 281 would be an invisible, cold and dark cloud, a ghost in space. The cluster provides both the illumination and the destructive force that carves the nebula into its recognizable shape. The relationship between the cluster and the nebula is not a peaceful one. It is a continuous battle. The same stellar winds that flow from these massive stars, carrying material away at millions of miles per hour, are actively sculpting and compressing the surrounding gas and dust. They have already blown a vast cavity around the cluster, which we see as the bright central region of the Pacman. The dark dust lane forming the mouth is the next frontier in this erosion process, a stubborn, dense ridge that is resisting dissolution. Over thousands of years, the radiation and winds from IC 1590 will continue to eat away at this dark material, slowly changing the Pacman's familiar profile. In some areas, this stellar pressure is triggering the collapse of other dense pockets within the cloud, potentially initiating the birth of a new generation of stars. This makes the entire region a fascinating laboratory for studying stellar feedback, demonstrating how the first generation of stars in a cluster can directly influence the conditions for and even trigger the birth of the next. Adding another layer of intrigue to this system is the presence of small, dark, and incredibly dense knots known as Bok globules. These are scattered throughout the nebula, appearing as tiny black teardrops against the glowing red background. These globules are the densest cores of the original cloud, so thick with dust that they are opaque even to the powerful radiation from the cluster. Within their shielded hearts, the pressure and density may be high enough for gravity to overcome all other forces, leading to the collapse that forms new stars. The Pacman Nebula offers a chance to observe these potential stellar incubators in a very active environment, showing us the various stages of star formation, from the cold, dark globules to the brilliant, newly ignited giants of IC 1590. It's a comprehensive picture of stellar evolution, all contained within one distinctive, playful-looking cosmic structure that continues to chomp its way through the interstellar medium. But from the playful chomping shape of the Pacman, we now turn our attention to a nebula whose scale is so immense it rivals a continent. At number 29 on our list is NGC 1499, the legendary California Nebula. Located in the constellation Perseus, this is a sprawling cloud of glowing hydrogen gas that, in wide-field astrophotographs, bears a striking and entirely coincidental resemblance to the outline of the US state of California. It's a beautiful example of pareidolia, the human tendency to see familiar shapes in random patterns, but on a truly cosmic canvas. The nebula is enormous, stretching over 100 light-years in length, meaning a beam of light would take more than a century to travel from one end to the other. Despite its vast size, it is notoriously difficult to observe visually through a telescope because its light is spread over such a large area, resulting in a very low surface brightness. It appears to the eye as a faint, ghostly smudge, but through the lens of a camera with long exposures, it transforms into a detailed and intricate structure of crimson gas, its silhouette unmistakably evoking the western coastline of North America. The reason this colossal cloud glows with such a distinctive red hue is a story of immense stellar power. The California Nebula is an emission nebula, which means it does not shine by reflecting starlight, but because its gas has been energized into a state of fluorescence. The source of this energy is not located within the nebula itself, but comes from a brilliant runaway star located just next to it. This is the hot blue giant star known as Xi Persei or Menkib. Xi Persei is a stellar powerhouse classified as an O-type star, one of the hottest and most massive categories known. Its surface temperature soars to an incredible 37,000 degrees Celsius, and it radiates most of its tremendous energy in the ultraviolet part of the spectrum. This star is essentially a colossal ultraviolet lamp, and the California Nebula is the cosmic gas cloud it illuminates. The physics at work here is both simple and profound. The intense ultraviolet photons streaming from Xi Persei smash into the neutral hydrogen atoms that make up the vast nebula. These high-energy collisions are so violent that they rip the electrons right off the hydrogen atoms, a process known as ionization. After a short time, these free electrons are recaptured by the hydrogen nuclei or protons. When this recombination happens, the electron releases energy, but it does so by emitting a very specific shade of deep red light. This specific wavelength is known to astronomers as hydrogen alpha, and it is the primary reason so many emission nebulae throughout the universe, from the Great Orion Nebula to the Lagoon, glow with that characteristic crimson color. The entire California Nebula is in effect a gigantic neon sign with Xi Persei as its power supply. The delicate filaments and variations in brightness we see within the nebula are a direct map of the density of the gas, showing where the cloud is thickest and where the ultraviolet radiation from the star is able to penetrate most effectively. What makes this system particularly fascinating is the motion of its illuminating star. Xi Persei is not sitting still. It is a runaway star hurtling through space at a tremendous speed. It is believed that this star was once part of a binary system in the nearby young cluster of Perseus OB2, and its companion star exploded as a supernova. The catastrophic disruption of that explosion likely kicked Xi Persei out of its birthplace, sending it speeding into interstellar space like a bullet. It is now plowing through this region of the galaxy, and its fierce radiation is essentially lighting up the interstellar medium it is passing through. We are seeing a chance encounter, a temporary and fleeting alignment between a speeding stellar torch and a vast, otherwise dark molecular cloud. In many ways, the California Nebula is a cosmic accident, a beautiful and photogenic coincidence that will eventually fade as the star moves away and the nebula's gas is dispersed or reshaped by other forces. This grand structure, which seems so permanent in our photographs, is actually a transient spectacle, a brilliant but short-lived chapter in the dynamic and ever-changing story of our galaxy. Continuing our exploration of the Cygnus region, we arrive at one of the most stunning and easily recognizable cosmic landscapes in the entire northern sky. At number 30 on our list, we find the sprawling NGC 7000, better known as the North America Nebula. Just a glance at a wide-field photograph reveals why it earned this name. Its outline is an uncanny match for the North American continent, complete with a prominent Gulf of Mexico, a dark Atlantic seaboard, and even a bright Florida-like peninsula. This celestial continent is so vast that its apparent size in our sky is 4 times larger than the full moon, and its true physical extent spans over 100 light-years. The sheer scale of this structure is a marvel in itself, but its origin story is even more fascinating, revolving around a single, hidden stellar powerhouse. The brilliant glow of the North America Nebula, like that of the California Nebula, comes from the process of ionization. Its characteristic red color is the light of hydrogen gas being energized by a torrent of ultraviolet radiation. For many years, the identity of the star responsible for this illumination was a mystery. The nebula itself appeared to be a void with no bright stars at its center. Astronomers eventually pinpointed the culprit as a brilliant hot star known as HD 199579. This star, however, is not situated in the middle of the continent. Instead, it lies just out of frame behind the dark, obscuring dust lane that forms the Atlantic coast of the nebula. This dense wall of dust, known as the Cygnus Wall, blocks the direct light from the star from our perspective, but allows its powerful ultraviolet radiation to flood over the top, lighting up the entire gaseous continent on the other side. We are witnessing a cosmic silhouette on a truly monumental scale, where a dark, intervening cloud creates a familiar shape by blocking the light from a brilliant, hidden energy source. Just off the coast of this cosmic continent lies our 31st strange object, IC 5070, the Pelican Nebula. At first glance, it appears to be a separate entity, a bird-like structure with a long beak and a curved neck. However, the North America and Pelican nebulae are not distinct objects at all. They are two parts of a single, gigantic interstellar cloud of ionized hydrogen. The same star, HD 199579, is illuminating both. The dark, dusty lane that separates them is what creates the illusion of two separate forms. From our vantage point on Earth, this dust cloud happens to fall in a pattern that carves out the shape of the Gulf of Mexico, with the Pelican Nebula appearing as if it is wading in the same cosmic waters. This intricate interplay of light and shadow demonstrates how much of what we see in the universe is a matter of perspective, a beautiful accident of our particular line of sight. The Pelican Nebula is far more than a static shape. It is a dynamic stellar nursery undergoing constant and dramatic change. The interface between the dark dust cloud and the bright gas, particularly in the region corresponding to the Pelican's neck and back, is a site of intense activity. Here, the radiation from the hidden central star is relentlessly eroding the dark molecular cloud, but in doing so, it is also triggering the birth of new stars. As the ionization front, the boundary between the hot, ionized gas and the cold, neutral gas advances into the cloud, it compresses the material. This compression can cause dense knots within the cloud to collapse under their own gravity, igniting into new protostars. These newborn stars then begin to carve out their own cavities and emit their own radiation, further altering the structure of the nebula. The Pelican Nebula is therefore a living ecosystem where the destructive power of starlight is simultaneously a creative force, shaping the nebula and spawning the next generation of suns in an ongoing cycle of stellar life and death. This entire complex, including both the North America and Pelican nebulae, is situated in one of the most fertile and turbulent regions of our Milky Way galaxy, the Cygnus X region. This area is a sprawling network of molecular clouds, stellar associations, and other nebulae, making it one of the most active sites of massive star formation in our galactic neighborhood. It is a testament to the sheer density of raw material available here that such colossal structures can form and be illuminated. To fully appreciate the context, we can briefly revisit our 23rd object, NGC 6960, the Witch's Broom Nebula, which is part of the Veil Nebula supernova remnant. This ancient explosion is also located in Cygnus, and while not physically connected to the North America and Pelican complex, its presence in the same patch of sky highlights the incredible diversity of cosmic phenomena that can coexist along a single line of sight. In one region, we see the glowing aftermath of a stellar death that occurred millennia ago, and in another, the brilliant glow of stellar nurseries where new stars are being born. This rich tapestry reminds us that the night sky is a palimpsest with the stories of birth, life, and death written one on top of the other, all contributing to the grand and continuous evolution of our galaxy. From the sprawling, continent-like forms of the North America Nebula, we now focus on a structure of stunning, almost artificial perfection. At number 33 on our list is NGC 7635, the astonishing Bubble Nebula. Floating in the vast expanse of the constellation Cassiopeia, this object presents one of the most visually striking and physically precise shapes in the cosmos, a nearly perfect, shimmering sphere of glowing gas that looks for all the world like a colossal soap bubble adrift in the void. This delicate, transparent shell, stretching 10 light-years across, is not a static sculpture, however. It is a dynamic and violent structure, a cosmic bubble being actively blown by the ferocious output of a single, extraordinary star at its heart. The brilliant architect of this celestial sphere is a massive Wolf-Rayet star known as SL20575. This is not a star like our Sun. It is a stellar rarity in an advanced and volatile stage of evolution. Wolf-Rayet stars are the exposed, helium-burning cores of stars that began their lives with truly immense mass, perhaps 20 times that of the Sun or more. They have shed their outer hydrogen envelopes through powerful winds, revealing their superheated interiors. The central star of the Bubble Nebula is a spectacular example, with a surface temperature soaring to around 35,000 degrees Celsius. It is this incredible heat that generates a relentless, supersonic stellar wind. The star is continuously ejecting its own atmosphere into space at a phenomenal speed of over 4 million miles per hour. This torrent of particles acts like a cosmic sandblaster, streaming outward in all directions and plowing into the surrounding, slower-moving material of the giant molecular cloud from which the star was born. The physics that creates the bubble's perfect form is a beautiful demonstration of pressure balance. The expanding shell of the bubble is not empty. It is a dense, gathered wall of interstellar material that has been swept up by the star's powerful wind, much like snow piling up in front of a plow. The immense outward pressure from the constant wind pushes against this shell, while the internal pressure from the hot gas trapped inside the bubble helps to maintain its structure. Meanwhile, the surrounding molecular cloud provides a uniform, resisting pressure from the outside. It is this delicate equilibrium between the outward push of the stellar wind and the inward pressure of the surrounding cloud that molds the shock front into such a remarkably spherical shape. The bubble expands because the pressure from within is slightly greater than the pressure from without, creating a stable, propagating shock wave that we see as the nebula's bright, sharp rim. Yet the universe is rarely perfectly uniform. The most captivating feature of the Bubble Nebula is the fact that its central star is not positioned at the exact center of the bubble. It is noticeably offset, drifting closer to one side of the glowing sphere. This seemingly minor detail reveals a profound story about the environment around the star. The reason for this offset is that the massive star is not floating in a perfect vacuum. It is moving through a complex and lumpy interstellar medium. The molecular cloud into which the bubble is expanding is not homogeneous. On the side where the star is closer to the edge, the cloud is less dense, allowing the stellar wind to expand more easily and rapidly. On the opposite, far side, the star is encountering a much denser, more resistant region of the cloud. The wind has to work harder to push into this denser material, resulting in a slower expansion rate and a thicker, brighter rim. This asymmetry provides a direct, visible map of the density variations in the star's environment, a snapshot of the complex and textured nature of the interstellar medium. The vibrant colors of the Bubble Nebula tell their own chemical story. The predominant reddish glow along the outer shell comes from ionized hydrogen gas, heated to incandescence by the intense ultraviolet radiation from the central star. However, the most striking feature is the brilliant electric blue glow that dominates the interior of the bubble, particularly on the left side. This luminous color is the signature emission of ionized oxygen atoms. The presence of this highly energized oxygen indicates the extreme conditions within the bubble. The material inside is not the pristine hydrogen of the original cloud. It is a mix of stellar wind material ejected directly from the Wolf-Rayet star itself, enriched with heavier elements like oxygen, carbon, and nitrogen that were forged in the star's core. This makes the Bubble Nebula more than just a kinetic sculpture. It is also a chemical factory, releasing newly synthesized elements into the galaxy that will one day be incorporated into new generations of stars and planets. The entire system is a brilliant illustration of stellar feedback, a process fundamental to galactic evolution. The massive central star, through its wind and radiation, is violently reshaping its immediate surroundings, clearing out a vast cavity. This process regulates star formation in its vicinity. By dispersing the gas, it can shut down the birth of new stars in that region. Conversely, the compression of the surrounding cloud at the bubble's edge can also trigger the collapse of dense pockets, potentially initiating the formation of a new generation of stars. The life of the Bubble Nebula is destined to be both brilliant and brief. The central Wolf-Rayet star is living on borrowed time, racing through its final evolutionary stages. In a cosmic instant, it will likely end its life in a spectacular supernova explosion, an event that will utterly obliterate the delicate bubble we see today. For now, however, it stands as a perfect celestial laboratory, a fleeting and beautiful demonstration of the powerful forces that a single, determined star can exert upon the fabric of space. Venturing far beyond the familiar star fields of our own Milky Way, we arrive at a stellar nursery of extraordinary clarity and significance. At number 34 on our list is NGC 602, a brilliant young star cluster situated not within our galaxy, but in the Small Magellanic Cloud, a satellite dwarf galaxy that orbits our own. This distant location is the key to its scientific importance. The Small Magellanic Cloud has what astronomers refer to as low metallicity. In this context, metals mean any element heavier than hydrogen or helium. This galaxy possesses a much smaller abundance of these heavy elements compared to the Milky Way, making it a closer analog to the conditions of the early universe when the first generations of stars were forming from pristine gas. NGC 602 offers us a pristine laboratory to study the process of star formation in this more primitive, unenriched environment, free from the complex chemistry that clouds similar processes in our own galactic neighborhood. The cluster itself is a spectacular sight, as revealed in stunning detail by the Hubble Space Telescope. It is a rich gathering of hot, young, massive stars, all blazing with intense blue-white light. These stellar infants are incredibly powerful, emitting a ferocious torrent of ultraviolet radiation and generating powerful stellar winds that stream outward at millions of miles per hour. This tremendous energy output is not contained. It is actively tearing apart the very pillar of gas and dust from which the cluster was born. The most iconic Hubble images show the cluster nestled right at the head of a vast, dark, finger-like projection of dust and gas, a structure that bears a striking resemblance to the famous pillars of creation in the Eagle Nebula, but viewed from a profoundly different cosmic perspective. What we are witnessing is a dramatic confrontation between the forces of creation and destruction. The radiation and winds from the central cluster are acting like a cosmic blowtorch, eroding the gaseous pillar and evaporating the smaller, gaseous globules that dot its surface. This process, known as photoevaporation, is literally boiling away the cloud. As the intense radiation strikes the dense gas, it heats the surface layers, giving atoms enough energy to escape the cloud's gravity and stream off into space. This creates the intricate, sculpted ridges and the wispy, veil-like structures that appear to be flowing away from the pillar. The entire scene is a snapshot of violent change, where the first brilliant acts of a star's life involve the systematic demolition of its own cradle. Yet, in a beautiful paradox, this destructive process is also a creative one. As the radiation-driven shock front advances into the pillar, it compresses the gas and dust ahead of it. This compression can trigger gravitational collapse in denser pockets within the cloud, potentially initiating the birth of a second generation of stars. This is a critical area of study around NGC 602. Astronomers are actively searching for evidence of these triggered protostars, still embedded within the dusty pillar and revealed only by observations in infrared light which can penetrate the obscuring dust. This would demonstrate a self-propagating star formation process, where one generation of stars directly incites the birth of the next, a chain reaction that could fundamentally shape how entire galaxies build their stellar populations. The low metallicity environment of the Small Magellanic Cloud adds a fascinating twist to this entire drama. With fewer heavy elements present, the dust grains in the nebula are different. They are smaller and less abundant than the dust grains found in Milky Way nebulae. This has a direct impact on the physics of the region. With less dust to block and absorb the intense starlight, the ultraviolet radiation from the massive stars can penetrate deeper into the cloud, potentially creating larger and more diffuse ionized regions. Furthermore, the process of cooling that allows a cloud to collapse and form stars relies partly on the presence of heavier elements. In a low metallicity cloud like this, the cooling is less efficient, which might affect the distribution of stellar masses that form, perhaps favoring the birth of more massive stars. By studying NGC 602, we are not just looking at a pretty cluster, we are peering back in time, gaining insights into how the very first star clusters in the universe may have formed and how they interacted with their primordial surroundings. It serves as a vital bridge connecting the familiar star-forming regions of our own galaxy to the ancient, metal-poor origins of cosmic structure itself. From the delicate, sculpted pillar of NGC 602 in a neighboring dwarf galaxy, we now turn our attention to a stellar nursery of such staggering scale that it dwarfs any similar region within our own Milky Way. At number 35 on our list, we encounter NGC 604, a cosmic powerhouse located within the graceful spiral arms of the Triangulum Galaxy, Messier 33. This is not merely a nebula, it is one of the largest and most luminous H2 regions known in the entire local group of galaxies. To grasp its immensity, consider that if you placed NGC 604 at the location of the famous Orion Nebula, it would outshine the planet Venus in our night sky, casting discernible shadows on the Earth below. Its sheer size is nearly 1,500 light-years across, a vast cavity of glowing gas energized by a stellar metropolis within, a brilliant testament to the explosive potential of concentrated star formation on a truly galactic scale. What makes NGC 604 such a compelling object for astronomers is the sheer concentration of stellar heavyweights it contains. Nestled within its glowing heart are over 200 recently formed stars of spectral class O and B, the most massive, hottest, and shortest-lived stars in the universe. This is a stellar association of unparalleled density. To put this in perspective, the magnificent Orion Nebula, the most famous stellar nursery in our sky, contains only a handful of such titans. The collective energy output from the stars in NGC 604 is phenomenal. Their combined ultraviolet radiation is so intense that it ionizes the surrounding hydrogen gas cloud, a structure over 100 times more massive than the Orion Nebula, causing it to glow with a brilliance visible across millions of light-years of intergalactic space. The nebula itself acts as a colossal beacon, signaling the presence of this ferocious stellar factory. The internal structure of this giant region, as revealed by the Hubble Space Telescope, is a complex and dynamic landscape. It is not a smooth, uniform bubble. Instead, it is filled with an intricate network of glowing filaments, vast, dark lanes of dust, and enormous, bubble-like cavities. These cavities have been blown clear by the combined stellar winds from the most massive stars, which flow outward like a perpetual hurricane, stripping away surrounding material and sculpting the nebula from the inside out. In several locations, you can see where these winds have collided with denser walls of gas, creating bright, sharp-edged ridges and shock fronts that glow brilliantly in the light of ionized hydrogen and oxygen. The entire region resembles a vast celestial coral reef, its delicate forms carved not by gentle ocean currents, but by the relentless, energetic output of hundreds of newborn suns. This intricate architecture provides a direct, visible map of the complex feedback processes between newborn stars and their natal cloud, showing how they simultaneously destroy their cradle while creating the conditions for future star formation at the nebula's crowded edges. The story of NGC 604 is also a tale of cosmic chemistry and future destiny. The intense radiation field within the nebula is so powerful that it creates several ionization fronts, boundary layers where the energetic ultraviolet light is actively dissociating molecules and stripping atoms of their electrons. Spectroscopic studies reveal a fascinating chemical composition within these fronts. The nebula is rich not only in hydrogen but also in heavier elements like helium, oxygen, and sulfur. The presence of these elements, forged in the hearts of previous generations of stars and scattered by supernova, enriches the interstellar medium of the triangulum galaxy. This chemical enrichment is a crucial part of galactic evolution, as this recycled material will one day become part of new stars, planets, and potentially the building blocks of life. The future of this stellar metropolis is both brilliant and brief. The most massive stars within it will live for only a few million years before ending their short, violent lives in supernova explosions. These blasts will further churn the nebula, seeding it with even heavier elements and likely triggering the collapse of nearby gas clouds to form a new, subsequent generation of lower-mass stars that may survive for billions of years, long after their brilliant progenitors have vanished. NGC 604, therefore, is more than a static wonder. It is a single, magnificent frame in the continuous film of galactic life, showing us the dramatic, explosive, and creatively destructive processes that build and reshape galaxies over cosmic time. Our exploration of cosmic neighbors now brings us to two fascinating but often overlooked members of our local galactic community, a pair of dwarf galaxies that orbit the mighty Andromeda Galaxy. At numbers 36 and 37, we have NGC 6822, better known as Barnard's Galaxy, and NGC 185. These two objects represent very different paths in galactic evolution, yet both hold crucial clues to understanding how the largest galaxies, like Andromeda and our own Milky Way, grow and influence their surroundings. First, let's turn our gaze to NGC 6822, Barnard's Galaxy. Located a little over 1.5 million light-years away in the constellation Sagittarius, this is a delightful example of an irregular galaxy. Through a telescope, it doesn't present the elegant spiral arms or smooth ellipse of its larger cousins. Instead, it appears as a faint, ragged patch of light, a cosmic cloud that seems to have been pulled and twisted into a disorganized but beautiful shape. This lack of a defined structure is the hallmark of an irregular galaxy, and Barnard's is one of the closest and brightest of its kind, a member of our local group. Its apparent chaos, however, is deceptive. Within this seemingly formless mass, there is a tremendous amount of activity. Barnard's Galaxy is a hotbed of star formation. Its interstellar medium is rich with neutral hydrogen gas, the raw fuel for creating new suns, and this gas is actively collapsing to form brilliant young stellar associations. What makes Barnard's Galaxy particularly special to astronomers is its low metallicity. Similar to the small Magellanic Cloud we discussed earlier, it contains a much smaller abundance of heavy elements compared to the Milky Way. This makes it a pristine laboratory for studying star formation in an environment that closely resembles the conditions of the early universe. The stars being born here are formed from material that has been less polluted by generations of previous supernova. This allows scientists to investigate the fundamental processes of star birth without the complicating factors of complex chemistry. Within its boundaries, you can find magnificent H2 regions, glowing clouds of ionized hydrogen that are often larger and more luminous than any found in our own galaxy. These stellar nurseries are creating massive hot stars that live fast and die young, their supernova explosions already beginning to seed the galaxy with the first heavy elements that will eventually enrich future generations of stars and planets. Barnard's galaxy is a living fossil, a glimpse into a more primitive and violent era of cosmic history, happening right in our own galactic backyard. Now let's contrast this with its companion, NGC 185. This galaxy, also orbiting Andromeda, presents a completely different picture. NGC 185 is a dwarf elliptical galaxy. Elliptical galaxies are typically thought of as cosmic retirement homes, vast, smooth, and featureless collections of old, red stars that have used up their gas and dust long ago and ceased forming new stars. They are the quiet, aging giants of the universe. For a long time, astronomers classified NGC 185 as just such a tranquil, red and dead system. But as observations improved, a surprising secret was revealed. Hidden within this population of ancient stars were clear signs of a much more recent and turbulent past. The first clue was the discovery of distinct, faint clouds of dust scattered across the body of the galaxy. Dust is a telltale sign of cold gas, the very material needed to form new stars, and it has no business being in an ancient elliptical galaxy where all such material should have been used up or blown away billions of years ago. Even more startling was the detection of a population of relatively young blue stars. These are stars that could not have been formed in the early universe. They must have been born in the last few 100 million years, a mere blink of an eye on cosmic timescales. This evidence points to a dramatic conclusion. NGC 185 experienced a recent burst of star formation, long after its primary period of stellar birth was thought to have ended. So, what could have stirred this dwarf galaxy from its slumber and triggered this late-life burst of activity? The most likely explanation involves its gravitational relationship with its giant neighbor, the Andromeda galaxy. As NGC 185 orbits Andromeda, the tremendous tidal forces from the larger galaxy may have compressed its remaining reservoirs of gas, initiating a final, brief episode of star birth. Alternatively, it's possible that NGC 185 merged with an even smaller, gas-rich dwarf galaxy, an event that would have provided a fresh infusion of fuel for new stars. This recent activity makes NGC 185 a crucial object for understanding the evolution of small galaxies. It demonstrates that even supposedly dead galaxies can have complex and eventful lives, with their star formation history being punctuated by late, unexpected bursts of creativity driven by their dynamic galactic environment. Adding another layer of intrigue to NGC 185 is the presence of its own globular cluster system. Globular clusters are dense, spherical collections of hundreds of thousands of ancient stars, and they are typically associated with massive galaxies. The fact that a small dwarf galaxy like NGC 185 possesses multiple globular clusters is a significant discovery. It suggests that this galaxy was much more massive and productive in the distant past, capable of forming and holding onto these dense stellar systems before it lost most of its gas and stars to its larger neighbor through tidal stripping. These clusters are like surviving relics from a more glorious era, orbiting the galaxy as permanent monuments to its former stature. When we look at the pair of NGC 6822 and NGC 185 together, we see a profound illustration of galactic diversity. One is a chaotic, gas-rich nursery actively building its future, while the other is a quiet elder that still bears the scars and surprises of a long and dynamic life. Both, however, are essential pieces in the puzzle of how giant galaxies like Andromeda assemble their entourage of satellites and how these smaller systems contribute to the rich tapestry of our local group. Now we turn from the dwarf galaxies orbiting Andromeda to a truly nomadic object much closer to home, yet in many ways far more remote. At number 38 on our list of strange objects is NGC 2419, a globular cluster that has earned the dramatic and fitting nickname the Intergalactic Wanderer. For many years after its discovery, its true distance was a profound mystery. Most globular clusters, those dense, spherical swarms of hundreds of thousands of ancient stars, orbit the central bulge of our Milky Way galaxy in a relatively compact halo. But NGC 2419 is different. It follows an immensely long, elliptical orbit that carries it hundreds of thousands of light years away from the galactic center, taking it on a journey that lasts nearly 3 billion years to complete. At its most distant point, this cluster ventures so far into the emptiness of intergalactic space that it is almost as close to the neighboring Andromeda galaxy as it is to our own. This extraordinary isolation immediately sparked the question, is this truly a member of our galaxy, or is it something else entirely, a cosmic drifter just passing through? The immense distance of NGC 2419 is the key to its strangeness. Located about 300,000 light-years from Earth, it is one of the most distant globular clusters known to be gravitationally bound to the Milky Way. To put that into perspective, it is more than 10 times farther away from us than the Large Magellanic Cloud, our most prominent satellite galaxy. When you look at this cluster through a powerful telescope, you are seeing light that began its journey to Earth around the time our earliest human ancestors were first learning to use stone tools. Its sheer remoteness means it appears incredibly faint and small in our sky, and for a long time, some astronomers even mistakenly classified it as a nearby star because it was so difficult to resolve into individual suns. Unlocking its secret required precise measurements of its variable stars, which confirmed its staggering distance and cemented its status as an extreme cosmic outlier. This bizarre orbital situation led to a compelling and long-standing hypothesis. Perhaps NGC 2419 is not a native of the Milky Way at all. The idea was that it could be the stripped core of a former dwarf spheroidal galaxy. In this scenario, a small galaxy, much like the ones we see orbiting Andromeda today, ventured too close to the youthful, more massive Milky Way billions of years ago. The overwhelming tidal forces of our galaxy would have then proceeded to tear the dwarf galaxy apart over eons, pulling away its outer stars and gas, which were then assimilated into the Milky Way's halo. All that would remain is the dwarf galaxy's heart, its dense, resilient central star cluster, which we now observe as NGC 2419, a celestial ghost continuing its vast, lonely orbit as the last remnant of a system that no longer exists. This would explain its great distance and unique path. It would be a fossilized relic from an ancient act of galactic cannibalism. However, more recent and detailed studies have complicated this fascinating story. When astronomers analyzed the chemical composition of the stars within NGC 2419, they made a surprising discovery. The stars showed a distinct and complex chemical signature, with a wide variation in the abundance of certain elements like oxygen and sodium. This specific chemical pattern is actually characteristic of the classic, largest globular clusters that were born alongside the Milky Way itself, not of the more chemically simple stars typically found in dwarf galaxies. This crucial piece of evidence tilted the scales, suggesting that NGC 2419 is indeed a genuine, albeit exceptionally distant, member of the Milky Way's own family of globular clusters. It did not originate in a devoured dwarf galaxy. It was likely born during the very formation of our galaxy over 13 billion years ago. So if it is a native cluster, how did it end up on such an extraordinary journey? The current leading theory involves a powerful gravitational slingshot. In the chaotic early universe, the nascent Milky Way was a tumultuous place, with large clumps of matter and smaller proto-galaxies constantly interacting. It is possible that NGC 2419 had a close encounter with another massive object, perhaps even the core of another small galaxy that was merging with our own. This gravitational interaction could have flung the cluster out onto its current immensely elongated orbit, like a stone launched from a catapult. Its path is so vast that it spends most of its cosmic life drifting in the desolate hinterlands between galaxies, a solemn sentry patrolling the remote frontiers of our galaxy's gravitational domain. It is a testament to the violent and dynamic processes that shaped our galactic home in its youth. Whether it is the corpse of a devoured dwarf or a native sun flung into the void, NGC 2419 remains a powerful symbol of isolation, a glittering city of ancient stars forever journeying through the immense and lonely dark. If you look up toward the constellation Centaurus on a clear, dark night, you might notice what appears to be a slightly fuzzy, out-of-focus star. To the naked eye, that's all Omega Centauri seems to be. But aim even a modest pair of binoculars or a small telescope in its direction, and that faint smudge blossoms into one of the most spectacular sights in the entire heavens. A colossal, glittering sphere of stars, so dense and bright it seems almost impossible. This is NGC 5139, the crown jewel of the Milky Way's globular cluster system. It is not merely the largest and brightest of its kind visible from Earth. It is a celestial anomaly of such proportions that it forced astronomers to reconsider its very nature. For decades, it was classified as just an unusually big globular cluster, but we now have compelling evidence that we are not looking at a simple cluster at all. We are witnessing the ghost of a galaxy, the devoured heart of a long-lost dwarf galaxy that was torn apart and absorbed by our own Milky Way in the deep cosmic past. What sets Omega Centauri apart, first and foremost, is its staggering scale. An average globular cluster might contain a few 100,000 stars. Omega Centauri contains well over 10 million stars, all gravitationally bound together in a space only about 150 light-years across. To stand on a hypothetical planet at its center would mean seeing a sky where night was an impossible concept, with tens of thousands of stars shining brighter than Venus does in our own sky, creating a perpetual, brilliant twilight. But its sheer size is only the beginning of the mystery. The most telling clues to its unique origin come from the stars themselves. In a typical globular cluster, all the stars were born at roughly the same time from the same primordial cloud of gas. They are like a single, ancient generation, all exhibiting very similar ages and chemical compositions. Omega Centauri utterly shatters this pattern. Detailed studies have revealed that its stars are not a single, homogeneous population. Instead, they represent multiple, distinct generations born over a span of billions of years. This is a discovery of profound significance. The stars within Omega Centauri show a wide and complex range of metallicities, that is, the abundance of elements heavier than hydrogen and helium. Some stars are extremely metal-poor, indicating they formed very early in the universe's history from pristine gas. Others contain significantly higher amounts of iron and other heavy elements, which could only have been forged in the nuclear furnaces of previous generations of stars and then scattered into the interstellar medium by supernova explosions. For a second and then a third generation of stars to form, a cluster must have held onto its gas for an immensely long time, something the relatively weak gravity of a standard globular cluster could never do. Only the deep gravitational well of an entire dwarf galaxy would have been capable of retaining this gas over such vast timescales, allowing for multiple separate epochs of star formation to occur. The chemical fingerprint of Omega Centauri stars is therefore a fossil record, telling the story of a system that was once massive enough to have its own complete, self-contained life cycle of stellar birth, death, and rebirth. Further evidence for this galactic cannibalism scenario comes from the cluster's motion and structure. Omega Centauri orbits the Milky Way on a path that is highly inclined and retrograde, meaning it moves in the opposite direction to the majority of the galaxy's rotation. This unusual orbit is a classic signature of an object that was captured, rather than one that formed in place. Additionally, the distribution of its stars is not perfectly smooth. Astronomers have detected faint stellar streams, tidal tails extending from the cluster, which are the ghostly remnants of stars that were stripped away during its violent, repeated close encounters with the Milky Way. The core of this devoured galaxy, being the densest part, managed to survive the tidal shredding, while its outer layers were torn off and assimilated into the Milky Way's halo. We are left looking at the galactic core that refused to be completely destroyed, a cosmic heart that still beats with the memory of its former self. Perhaps the most tantalizing piece of this puzzle lies hidden at the very center of this stellar metropolis. For years, astronomers have tracked the movements of stars swirling around the core of Omega Centauri, and they have found something peculiar. The stars at the very center are moving at unexpectedly high velocities, zipping around as if under the influence of an immense but invisible gravitational anchor. The most plausible explanation for this is the presence of an intermediate mass black hole, a celestial object with a mass of roughly 40,000 times that of our Sun. This class of black hole occupies a mysterious middle ground between the stellar mass black holes formed from collapsing stars and the supermassive monsters that lurk in the centers of galaxies. Its proposed existence at the heart of Omega Centauri is the final, compelling piece of evidence for its galactic origin. A black hole of this mass is exactly what you would expect to find at the center of a dwarf galaxy. It is the dormant engine that once powered a much larger and more complex system. The search for definitive proof of this black hole continues, but its potential presence transforms our view of Omega Centauri from a spectacular cluster into something far more significant. A direct, accessible laboratory for studying the building blocks of galaxy formation and the dark remnants they leave behind. It is a glittering relic from a time of cosmic construction, a surviving witness to the Milky Way's violent and acquisitive history. Having explored the galactic graveyard of Omega Centauri, we now shift our gaze to the most furious stellar factory in our entire corner of the universe. At number 40 on our list is NGC 2070, the breathtaking Tarantula Nebula. Located not within our Milky Way, but in our neighboring satellite galaxy, the Large Magellanic Cloud, this object is so immense and so brilliant that if it were placed at the same distance as the Orion Nebula, a mere 1,500 light-years away, it would cast sharp shadows on the Earth at night and be visible as a colossal, glowing cloud even during the daytime, spanning an area larger. 60 full moons in our sky. That staggering fact alone sets the stage for understanding that we are dealing with a phenomenon of an entirely different magnitude. The tarantula is not just a nebula, it is a super-star cluster still embedded within its own spectacular gaseous womb. A region of space where the forces of creation have been unleashed on a scale that is almost incomprehensible. The sheer statistics of the Tarantula Nebula are enough to defy belief. It spans over 1,000 light-years across, making it the largest and most luminous stellar nursery in our entire local group of galaxies. At its heart lies the colossal star cluster known as R136, a dense metropolis of stellar titans that contains some of the most massive and luminous stars ever catalogued. This includes stars like R13601, a behemoth with an estimated mass of over 250 times that of our Sun, pushing the very theoretical limits of how massive a star can be. The combined ultraviolet radiation flowing from this central cluster is so ferocious that it ionizes the surrounding gas cloud, causing it to glow with a brilliance visible across millions of light-years. But this intense light is more than just a beacon. It is a destructive and creative force. The radiation and powerful stellar winds from these massive stars are constantly sculpting the nebula, blowing vast bubbles and carving out intricate pillars and filaments that give the tarantula its spidery, sprawling appearance. In some places, this erosion is triggering the collapse of nearby gas clouds, sparking the birth of new stars, while in others, it is outright obliterating potential stellar nurseries. The entire region is a dynamic, chaotic ecosystem, a cosmic battle between gravity and radiation playing out on a truly epic scale. To fully appreciate the unique nature of the tarantula, it is illuminating to compare it with the most famous stellar nursery within our own Milky Way, which brings us back to our number 25 object, NGC 3372, the Eta Carinii Nebula. Both are colossal H2 regions, both are powered by incredibly massive stars, and both are stunningly beautiful. Yet they represent different tiers in the hierarchy of cosmic creation. The Eta Carinii Nebula is a magnificent and vast structure, stretching over 200 light-years, and it is dominated by the single, unstable hypergiant star system of Eta Carinii itself. That system is a cosmic time bomb, capable of ejecting 10 solar masses of material in a single event and threatening to explode as a hypernova. It is a spectacular example of a stellar nursery that has produced one of the most extreme and rare stellar objects known. However, when placed side by side with the tarantula, the differences in scale and intensity become starkly apparent. The Eta Carinii Nebula is a spectacular neighborhood of star formation. The Tarantula Nebula is an entire city, a veritable metropolis of stellar birth. The central cluster of the tarantula, R136, contains dozens of stars that are each as massive and powerful as Eta Carinii, all concentrated in one relatively small region. The energy output is not dominated by one or two singular stars, but by a vast collection of them, creating a sustained, frenetic environment of creation and destruction that far surpasses the activity in Carina. Furthermore, while the Eta Carinii Nebula is home to one recent famous eruption, the great eruption of the 1840s that created the homunculus nebula, the tarantula has witnessed stellar cataclysms on a grander scale. Within its boundaries lies the remnant of supernova 1987A, the closest observed supernova since Kepler's star in 1604. This event provided astronomers with an unprecedented front-row seat to the death of a massive star and the creation of a neutron star, all within this single hyperactive complex. This comparison highlights a fundamental aspect of galactic ecology. The large Magellanic Cloud, the tarantula's home, has a lower abundance of heavy elements compared to the Milky Way. This primitive chemical environment, much like we saw in Barnard's galaxy, is thought to be more conducive to the formation of the very highest mass stars. With less metal content, the processes of gas cooling and fragmentation work differently, potentially allowing gas clouds to collapse into more massive and luminous stellar embryos. The Tarantula Nebula is, therefore, not just a bigger version of what we have in our own backyard. It is a unique window into the conditions that were more common in the early universe, when the first generations of stars, known as population 3 stars, are believed to have formed. These primordial stars were likely monsters of several hundred solar masses, and while we cannot observe them directly, studying the tarantula gives us our best available proxy for understanding the environments that spawned them. It is a living laboratory that allows us to test theories about the upper limits of star formation and the feedback processes that regulate how galaxies evolve. Where the Eta Carinii Nebula shows us the dramatic life and impending death of a single, colossal stellar system, the Tarantula Nebula reveals the relentless, large-scale industrial activity that forges the very fabric of galaxies, demonstrating that the most intense cosmic dramas are often playing out in the smaller, satellite galaxies that orbit our own. But to witness a spiral galaxy where every element of its structure is amplified to an almost perfect extreme, we must turn our attention to the southern constellation of Fornax. Here at number 42 on our list, we find NGC 1365, a barred spiral galaxy so magnificent and archetypal it is often called the Great Barred Spiral Galaxy. This is not just another pretty face in the cosmos. It is a quintessential example of its class, a cosmic whirlpool where the graceful dance of stars, gas, and dust is orchestrated by the immense gravitational pull of a central bar, and where the core itself harbors a secret of unimaginable density and power. From the moment you see an image of NGC 1365, its defining characteristic is unmistakable: a brilliant, orange-colored bar of ancient stars that slices directly through the galaxy's center. This bar is not a minor feature. It is the galaxy's dominant gravitational backbone, a vast structure that acts as a cosmic funnel, channeling interstellar gas and dust from the sprawling outer arms inward toward the galactic core. This relentless flow of raw material is the engine behind the galaxy's vibrant and dramatic appearance, fueling both a firestorm of star formation and the insatiable appetite of the supermassive black hole that resides at its very heart. The spiral arms of NGC 1365 erupt from the ends of this central bar with stunning clarity and symmetry. Unlike the fragmented and patchy arms of some spirals, these are majestic, well-defined arcs that sweep outward, tracing perfect logarithmic spirals. They are a study in contrasting colors and processes. The regions closer to the bar and the core glow with a reddish-yellow light, the combined glow of billions of older, cooler stars. But as your eye follows the arms outward, they become alive with the brilliant blue light of countless young, massive stars and the telltale pink glow of vast hydrogen clouds, known as H2 regions, where new stars are actively being born. This is where the bar's gravitational influence pays its most visible dividend. The gas funneled inward by the bar becomes compressed, particularly at the ends of the bar and the inner sections of the spiral arms. This compression triggers the collapse of giant molecular clouds, igniting starbursts of incredible intensity. These stellar nurseries are some of the most active known in any nearby galaxy, creating dazzling clusters of hot, luminous stars that flood their surroundings with ultraviolet light and powerful stellar winds, shaping the nebula around them in an ongoing cycle of creation and destruction. Yet, the most profound consequence of this relentless inward flow of gas is not the birth of new stars, but what happens to that material when it reaches the very center of the galaxy. Lurking in the core of NGC 1365 is a supermassive black hole, an object with a mass estimated to be about 2 million times that of our Sun. In many galaxies, such a black hole would be a dormant, sleeping giant, but in NGC 1365, it is wide awake and feasting. The constant stream of gas channeled by the bar provides a continuous supply of fuel. As this gas spirals down toward the event horizon, it does not fall in directly. Instead, it forms a rapidly rotating, superheated structure called an accretion disk, where friction and immense gravitational forces heat the material to millions of degrees, causing it to glow with a blinding intensity across the entire electromagnetic spectrum, from X-rays to radio waves. This active galactic nucleus makes NGC 1365 a prime target for astronomers working with some of the world's most powerful telescopes. Observations from the NASA Chandra X-ray Observatory have been particularly revealing, detecting the searing X-ray emission from the multimillion-degree gas in the immediate vicinity of the black hole. These observations have provided compelling evidence for the black hole's rapid spin, a crucial property that affects how it interacts with space-time and influences its entire surroundings. Meanwhile, the Hubble Space Telescope and ground-based observatories have studied the brilliant clusters of newborn stars in the spiral arms and the complex dust lanes weaving through the galaxy's disk. By combining these different views, the visible light of the stars, the infrared glow of the dust, and the high-energy X-rays from the core, astronomers can piece together a complete picture of the galaxy's life cycle. They can see how the large-scale structure of the bar governs the small-scale physics at the galactic nucleus, directly linking the graceful motion of the spiral arms to the violent, high-energy processes happening at the very edge of a black hole. NGC 1365 stands as a perfect cosmic laboratory, a unified system where the flow of matter on a galactic scale directly powers one of the most extreme phenomena in the universe, demonstrating the profound interconnectedness of cosmic evolution. Yet while the Great Barred Spiral NGC 1365 shows us the dynamic potential of this structure at a grand scale, there exists a galaxy that serves as the quintessential textbook prototype of the form. At number 43 on our list, we encounter NGC 1300, a barred spiral so perfectly constructed and beautifully symmetrical that it has become the definitive cosmic poster child for its entire class. Located in the constellation Eridanus, this galaxy presents an almost impossibly ideal face on view to us, offering a pristine and unobstructed look at the intricate mechanics that govern these celestial whirlpools. Its bar is not a subtle feature, it is a bold, luminous backbone of ancient yellow stars that cuts decisively across the galaxy's center. From the graceful, tapered ends of this bar, two magnificent spiral arms unfurl in an exquisitely tight and sweeping pattern, winding their way outward into the darkness. These arms are not the loose, fragmented scraps seen in some spirals. They are grand design arms of the highest order, long, continuous, and dusted with the brilliant blue light of young stellar associations and the faint pink glow of star-forming regions. It is a galaxy that appears both serene and perfectly engineered, a cosmic mechanism frozen in a state of beautiful balance. The true purpose of that prominent central bar, however, is anything but static. It functions as the galaxy's primary gravitational engine, a vast rotating structure that fundamentally controls the flow of material within the galactic disk. Unlike in a simple spiral where gas and dust orbit the center in relatively circular paths, the bar creates a powerful non-axisymmetric gravitational field. Think of it as a cosmic traffic circle, but one that systematically directs incoming material toward the central city. As stars and gas clouds orbit the galaxy, their paths are decisively altered when they encounter the bar's immense gravitational influence. The bar's rotation effectively sweeps up material from the outer disk, channeling it inward along dramatic, elongated orbits that run parallel to the bar itself. This creates a continuous and efficient funnel, a gravitational pipeline that transports the primary fuel for star formation, cold molecular hydrogen gas, from the galaxy's outskirts directly toward its crowded core. This inward flow is not a gentle drift, it is a dynamic process that compresses the gas, shock heating it and making it more likely to collapse under its own gravity. This is why we often see such intense bursts of star formation at the very ends of the bar and at the beginning of the spiral arms. These are the terminal points of the bar's delivery route, where the incoming gas piles up, becomes densely compressed, and ignites into brilliant stellar nurseries. This raises a fascinating and critical question. If the bar is so effective at funneling gas inward, what ultimately happens to all that material when it reaches the very center? Does it simply accumulate into a vast central star cluster, or does it continue its journey to an even more extreme fate? This is where the connection to active galactic nuclei and supermassive black holes becomes paramount. In many galaxies, the relentless inflow driven by the bar is believed to be the primary mechanism for feeding the monster lurking at the core. As the gas is driven inward, it can lose angular momentum and spiral ever closer to the central black hole, potentially falling into an accretion disk and lighting up the galactic nucleus with tremendous energy. Yet, NGC 1300 itself presents a curious and instructive twist on this narrative. Despite its magnificent bar and the clear evidence of gas inflow, its central region is surprisingly quiescent. Its nucleus is not a blazing active galactic nucleus. It is a relatively calm and normal galactic core. This tranquility offers a vital clue to astronomers, suggesting that the relationship between bars and black holes is not always straightforward. The secret may lie in the detailed structure of NGC 1300's very center. High-resolution images from the Hubble Space Telescope reveal that within the large primary bar, there is a second, smaller bar, a nuclear bar, oriented at a different angle, and within that, a distinct spiral pattern etched right into the heart of the galaxy on a scale of just a few hundred light-years. This phenomenon, known as nested bars or as a nuclear spiral, indicates that the process of transporting gas is a multi-stage affair. The large primary bar efficiently drains gas from the outer disk and deposits it into a circumnuclear reservoir around the core. However, getting that gas from this reservoir the final few dozen light-years down to the black hole's event horizon requires a separate mechanism. The smaller nuclear bar may be responsible for this final leg of the journey, and in NGC 1300, this secondary system may be inefficient or temporarily dormant. This means the central black hole is currently on a strict diet, receiving only a trickle of fuel despite the bounty of gas delivered to its galactic neighborhood. This makes NGC 1300 a perfect control subject, a galaxy that shows us the full infrastructure for feeding a central engine, but one where the final switch has not yet been flipped, allowing us to study the conditions that lead to black hole activity versus quiet retirement. Ultimately, NGC 1300 serves as far more than just a beautiful example of a common galaxy type. It is a fundamental reference point, a Rosetta Stone for understanding the life cycle of disk galaxies. Its flawless structure allows astronomers to test sophisticated computer models of how bars form, evolve, and interact with their host galaxies over billions of years. These models suggest that bars are not permanent fixtures. They may be transient, dynamic structures that can form and dissolve over cosmic time, often stirred up by gravitational interactions with other galaxies or by the gravitational instabilities within the disk itself. The presence of a strong bar like the one in NGC 1300 signifies a mature, settled galaxy that has undergone significant internal evolution. By studying this cosmic archetype in exquisite detail, we gain profound insight into the self-regulating mechanisms that govern galactic evolution, the intricate dance between large-scale structure and small-scale physics, and the universal processes that shape the majestic spiral universes we see scattered throughout the cosmos. Now, for something truly invisible yet overwhelmingly present, we turn our attention to a different kind of cosmic mystery, one that surrounds entire galaxies like a ghostly fortress. Our next two strange objects, numbers 44 and 45, are the isolated elliptical galaxies NGC 4555 and NGC 720. At first glance, these galaxies might seem like fairly ordinary residents of the universe. They are not caught in dramatic collisions, nor do they boast brilliant spiral arms. They are essentially giant spheres of ancient stars quietly coasting through the cosmic void. But their profound significance lies not in what we can see, but in what we cannot, and in a startling paradox that revealed itself only when we looked at them with X-ray vision. These solitary giants were found to be enveloped in gigantic, searingly hot atmospheres of gas, a discovery that provided some of the most compelling early evidence for the existence of vast, massive halos of dark matter surrounding individual galaxies. Let's first consider NGC 4555. This galaxy is classified as an isolated elliptical, meaning it floats in a relatively empty region of space, far from the bustling crowds and gravitational tug-of-war of a large galaxy cluster. For a long time, astronomers believed that such isolated ellipticals might be simple, even somewhat boring, objects. Without the constant gravitational harassment from neighbors, it was thought they might have a more placid history and a less complex structure. The first clue that something was deeply unusual came from observations with NASA's Chandra X-ray Observatory. When scientists pointed this powerful telescope at NGC 4555, they didn't just see the faint glow of old stars, they detected an immense spherical cloud of multimillion-degree gas enveloping the entire galaxy. This was a colossal and completely unexpected discovery. This hot gas halo was vast, stretching far beyond the visible starlight, and it posed an immediate and serious problem. The issue was one of simple gravity. A cloud of gas that hot has an enormous amount of thermal energy. The individual particles in that gas are moving at tremendous speeds, and for the cloud to remain bound to the galaxy, for it not to simply evaporate into intergalactic space, the galaxy's gravitational pull has to be incredibly strong. When astronomers calculated the mass of the visible stars in NGC 4555, they found it was nowhere near sufficient to provide the gravity needed to hold onto this roaring, superheated atmosphere. The stars alone were far too lightweight. Their collective gravity was like a weak hand trying to grip a powerful, struggling animal. The gas should have escaped billions of years ago. The inescapable conclusion was that there had to be a huge amount of additional mass present, mass that was completely invisible to telescopes. This missing mass, exerting a powerful gravitational pull, was the only thing that could be confining the giant cloud of hot gas. That invisible mass is what we call dark matter. Our second object, NGC 720, provides an even more detailed and revealing case study. Like its cousin, it is an isolated elliptical galaxy, and it too was found by the Chandra Observatory to be embedded in a gigantic hot gas halo. But the data for NGC 720 was so precise that it allowed astronomers to map the shape of this dark matter halo in a way that was groundbreaking. The hot gas, being a fluid, naturally settles into a shape that precisely traces the contours of the galaxy's overall gravitational field. Think of it like a glowing liquid filling an invisible container. By meticulously measuring the distribution and temperature of the gas, scientists could essentially use it to weigh the galaxy and, more importantly, to determine the shape of the container holding it in. What they found was astonishing. The dark matter halo surrounding NGC 720 was not a round sphere. It was flattened, almost like a gigantic, invisible flying saucer enveloping the galaxy. This discovery of a flattened or oblate dark matter halo was a critical piece of evidence. It helped rule out certain alternative theories for the missing mass, such as massive compact halo objects or MACHO, which would include things like black holes or neutron stars. A population of such discrete, point-like objects would tend to produce a more spherical gravitational field. The flattened shape observed around NGC 720, however, was perfectly consistent with the predictions for cold dark matter, a type of matter that does not interact with light and consists of slow-moving exotic particles. This provided strong, indirect support for the now standard cosmological model, confirming that dark matter forms vast, structured halos around galaxies, shaping the very space in which visible matter resides. The story these two galaxies tell is profound. They demonstrate that dark matter is not just a curiosity of massive galaxy clusters, where its effects are amplified by the sheer number of galaxies. Instead, it is a fundamental and ubiquitous component of every galaxy, a hidden scaffold upon which the visible universe is built. The presence of these massive dark halos around isolated galaxies like NGC 4555 and NGC 720 proves that dark matter is an integral part of a galaxy's identity from its very formation. It is the dominant gravitational force that gathers the initial gas, guides the assembly of stars, and provides the deep gravitational well that can trap and hold onto a seething atmosphere of hot gas for billions of years. These seemingly quiet, isolated ellipticals are, in reality, cosmic touchstones. They offer a clean, controlled environment to study dark matter, free from the complicating factors of galactic collisions and cluster dynamics. They remind us that the universe is dominated not by the glittering stars we see, but by the immense hidden architecture of dark matter, an invisible ocean in which every galaxy is merely a visible island. Yet, even the isolated giants we've just explored seem to inhabit a realm of serene solitude compared to the chaotic, overcrowded metropolises of the cosmos, the immense galaxy clusters. And to witness the absolute monarch of such a domain, we journey to the constellation Coma Berenices, where we find Object 46 on our list, NGC 4889. This is not merely a galaxy, it is a supergiant elliptical, the brightest and most dominant galaxy at the very core of the sprawling Coma cluster, a gathering of over 1,000 galaxies bound together by gravity. To the eye, it appears as a smooth, featureless, golden-yellow ellipsoid, a cosmic egg floating in a sea of smaller, fainter specks of light. But this serene appearance is a grand illusion. NGC 4889 is a gravitational titan, the ultimate product of a relentless, multi-billion-year campaign of cosmic cannibalism, and it harbors a secret at its heart that pushes the very limits of what we thought was possible. One of the most massive black holes ever detected in the known universe. The environment of the Coma cluster itself is key to understanding this galaxy's monstrous nature. Imagine a region of space so densely packed with galaxies that they are separated by only a few 100,000 light-years, compared to the millions of light-years that typically separate major galaxies like Andromeda and our Milky Way. This is a celestial megalopolis, and at its very center lies NGC 4889, the undisputed downtown. In such a crowded environment, the rules of galactic life are brutal. The immense collective gravity of the cluster creates a powerful tidal force, and as smaller galaxies swing past the central giant on their orbits, they are stretched and torn apart. Their stars are stripped away and added to the growing halo of the dominant galaxy, while their gas is funneled inward. This process, known as galactic cannibalism, is how a galaxy like NGC 4889 grows to such an incomprehensible size. It has spent eons consuming its smaller neighbors, growing fat on a steady diet of passing galaxies to become the behemoth we see today. Its smooth, symmetrical shape is the direct result of this violent history. The random orbits of all the absorbed stars have smoothed out into a featureless, swelling sphere, the final form of a galaxy that has conquered its entire local universe. But the most staggering product of this endless feast lies hidden deep within its core. After meticulous observations and complex measurements of the velocities of stars whipping around the galactic center, astronomers were able to calculate the mass of the supermassive black hole residing there. The result was almost beyond belief, a black hole with a mass of 21 billion times that of our Sun. To grasp this scale, consider that the event horizon of this monster, the point of no return for light, would extend far beyond the orbit of Pluto, engulfing our entire solar system with ease. This is a gravitational sinkhole of almost unimaginable proportions, a void so massive that it dominates the motion of stars across thousands of light years. What is truly fascinating, however, is that this Leviathan is currently dormant. It is a sleeping giant. The era of violent feasting that built it is largely over. Most of the available gas in its immediate vicinity has already been consumed or blown away by past outbursts, leaving the black hole in a state of quiet retirement, its unimaginable gravitational potential now largely silent, its accretion disk a faint and cold remnant of a more violent youth. This presents a captivating paradox. How can such a monstrously powerful object be so quiescent? The answer lies in the very nature of these brightest cluster galaxies. They represent a final, stable state in galactic evolution. The frantic cannibalism that built them also serves to deplete the fuel supply in their core regions. With less and less gas being funneled inward to form an accretion disk, the black hole's engine has little to feed on and therefore generates very little light or heat. This dormancy is actually a critical part of the feedback cycle that governs galaxy clusters. When such a black hole is active, its tremendous energy output can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. In its quiet state, it allows the galaxy to enter a long, stable retirement, filled with ancient red stars and largely devoid of the brilliant blue stellar nurseries seen in spiral galaxies. NGC 4889 and its central black hole stand as the ultimate example of this final evolutionary stage. They show us the end result of unopposed gravitational dominance, a magnificent, quiet, and unimaginably massive kingdom where the king, though currently at rest, possesses a power that is truly astronomical. But if the supergiant galaxy NGC 4889 represents the end result of galactic cannibalism, our next object presents a story of almost monastic isolation, a galaxy that has stubbornly resisted change for nearly the entire history of the universe. At number 47 on our list, we encounter NGC 1277, a compact, reddish, and incredibly dense galaxy soaring through the Perseus cluster. At first glance, it might seem unremarkable, a small and faint smudge of light. Yet, this galaxy is one of the most significant astronomical discoveries of recent years, a cosmic fossil that has survived for over 10 billion years virtually unchanged. It is what astronomers call a relic galaxy, a pristine time capsule from the universe's violent youth, and locked within its ancient heart is a secret so massive it has sent theorists back to their drawing boards. The concept of a relic galaxy is fascinating in itself. Most large galaxies, like our own Milky Way, have grown gradually over time through a series of mergers and acquisitions, swallowing smaller dwarf galaxies and, in some cases, colliding with other major galaxies to build their mass. This process constantly stirs up a galaxy's structure, triggering new waves of star formation and altering its fundamental character. NGC 1277, however, took a different path. It formed in a single, incredibly intense burst of star formation during the first billion years after the Big Bang. In a cosmically brief frenzy, it converted virtually all of its primordial gas into stars, and then it simply stopped. For reasons that are still not entirely clear, it never experienced another major merger. It never accreted significant new gas to fuel subsequent generations of stars. It has been floating through the crowded Perseus cluster for eons, a celestial hermit that has passively witnessed the chaotic galactic collisions happening around it without ever participating. The stars within it are therefore uniformly ancient, over 10 billion years old, making it a living museum of the universe's first epoch of galaxy building. This pristine state makes NGC 1277 an invaluable laboratory. By studying it, astronomers get a direct look at what the earliest fully formed galaxies were like. Its structure is a clue to the conditions of the early universe. It is a red and dead galaxy in the truest sense, not because it has aged and used up its fuel, but because it effectively lived its entire life in a single, brilliant flash and then entered a state of suspended animation. Its compact size and immense stellar density, packing roughly twice the number of stars as our Milky Way into a volume that is only a fraction of the size, is a hallmark of those first-generation galaxies which formed when the universe was much denser. Finding such a relic so close to us in cosmic terms is like finding a living dinosaur roaming a modern forest. It offers an unprecedented opportunity to study the properties of the ancient universe without having to peer to its very edge. However, the truly paradigm-shifting discovery about NGC 1277 lies at its very center. When astronomers set out to measure the mass of its central supermassive black hole, they expected to find an object consistent with the well-established scaling relationships that link a galaxy's size to the mass of its black hole. In most galaxies, the central black hole makes up a relatively small fraction of the total galactic mass, typically around 1/20%. The results from NGC 1277 were nothing short of astonishing. The black hole at its core is a behemoth weighing in at a staggering 17 billion solar masses. This single object constitutes a colossal 14% of the entire galaxy's stellar mass. To understand how utterly bizarre this is, imagine if a single organ, like your heart, made up 14% of your entire body weight. This proportion is thousands of times larger than the ratio found in the Milky Way or in any other known galaxy of a similar size. This discovery directly challenges one of the leading models of galaxy evolution, which posits that galaxies and their black holes grow in lockstep through a series of mergers. If NGC 1277 has been isolated since its formation, how did its black hole become so disproportionately huge? The relic status of the galaxy suggests the black hole did not grow through later mergers. It must have been born this way or grown to this immense size during that initial, furious burst of star formation. This points to a dramatic possibility. In the early universe, the rules for building black holes may have been fundamentally different. Perhaps the first supermassive black holes formed directly from the collapse of immense clouds of primordial gas, seeding galaxies with giants from the very beginning. Alternatively, the process that fed the black hole during the galaxy's starburst phase may have been extraordinarily efficient, allowing the black hole to gorge itself on the available fuel far more effectively than the galaxy could form stars. NGC 1277 forces us to reconsider the intricate dance between a black hole and its host galaxy. It suggests that the co-evolution we observe in the modern universe might not be the only path, and that the ancient cosmos was a place where true monsters could be forged in a single, rapid, and cataclysmic event. This ancient relic, therefore, is more than just a fossil. It is a profound cosmic anomaly, a single data point that holds the potential to rewrite our understanding of how the most massive objects in the universe first came to be. But for a planetary nebula that seems to possess a cosmic heartbeat, we must turn our attention to the next object on our journey. At number 49 on our list is NGC 1501, a planetary nebula located in the constellation Camelopardalis. At first glance, it appears as a bright, slightly oval disk, often nicknamed the Oyster Nebula for its textured, pearl-like appearance in photographs. But its true strangeness is not immediately visible to the eye. It is revealed through careful measurement over time. The entire nebula, this vast shell of gas light years across, undergoes subtle but detectable changes in its brightness. This is not a slow, steady dimming, but a rapid flickering, a pulsation that cycles in a matter of mere minutes. The source of this rhythmic change is once again the central star, but this one is a truly unique and hyperactive stellar remnant. The central star of NGC 1501 is a pulsating variable white dwarf, one of the most rapid of its kind known. It belongs to a rare class known as PG 1159 stars, named after the prototype of this group. This white dwarf is not just hot, it is going through a violent and unstable phase of its early cooling. It pulsates, rhythmically expanding and contracting its outer layers like a colossal cosmic bell. With each pulsation, its temperature and brightness change dramatically. These pulsations are incredibly fast, with the star completing a full cycle brightening and dimming in just under 2.5 minutes. This rapid flickering of the central engine has a direct and fascinating effect on the nebula it illuminates. The intense ultraviolet light that powers the nebula's glow fluctuates in sync with the star's pulsations. While the nebula itself is too large to change its physical structure on such a short timescale, its emitted light does very subtly as the changing ultraviolet flux from the star alters the ionization state of the gas. We are witnessing a real-time demonstration of energy transfer, where the frantic vibrations of a tiny, dense star send ripples of change through a structure trillions of miles wide. The existence of such a pulsating central star provides astronomers with a powerful natural tool. The study of stellar pulsations is known as asteroseismology, and it works much like how geologists use earthquakes to probe Earth's interior. The specific frequencies at which the white dwarf pulsates are directly tied to its internal structure, its mass, the thickness of its outer layers, and its rate of cooling. By meticulously recording the light variations of this star, scientists can essentially take an ultrasound of a white dwarf, peering into its deep interior to test theories about matter under extreme densities and the final stages of stellar evolution. The presence of a possible binary companion in this system adds another layer of intrigue. While not yet conclusively proven, the complex structure of the nebula, with its intricate, clumpy bubbles and anisotropic outflows, strongly suggests that the gravitational influence of a second star played a role in shaping the nebula and perhaps even in triggering the pulsations we see today. Together, NGC 246 and NGC 1501 offer two different but equally compelling portraits of binary influence in the final act of a star's life. One shows us a visible partnership in the quiet aftermath of death, while the other reveals a frantic, vibrating remnant whose energetic throbbing continues to orchestrate the light of its own magnificent tomb. And so we reach the final and one of the most dynamically fascinating entries in our cosmic catalogue of curiosities, number 50, NGC 7027. From the moment it was first resolved, this object stood out. It doesn't present the large, ethereal wings of the Butterfly Nebula or the intricate, concentric rings of the cat's eye. Instead, it appears as a brilliantly luminous, almost impossibly dense, and bizarrely shaped knot of light, often described as an insect in a cocoon or a microscopic organism magnified to a cosmic scale. This is a planetary nebula in its infancy, a stellar funeral shroud that is still being woven at a ferocious pace right before our eyes. Its exceptional brightness and compact nature have made it a premier laboratory for astronomers, a place where we can witness the complex and violent processes that occur in the first frantic moments after a star sheds its skin and begins its final transformation into a white dwarf. What makes NGC 7027 so compelling is its intricate and multi-layered bipolar structure. High-resolution images from the Hubble Space Telescope reveal a stunningly complex architecture. At its heart lies a bright, elongated central bar, which is likely a dense torus or ring of dust and gas surrounding the central star. Emanating from this bar are two distinct sets of lobes. There is an older, fainter, and more spherical outer shell, which represents the initial, slower ejection of the star's atmosphere. But contained within this is a much younger, brighter, and more elongated inner structure, expanding outward at tremendous speeds. This nested configuration is like a fossil record of two distinct eruptive phases, giving us a clear timeline of the star's death throes. The entire system is a testament to the fact that a star's demise is not a single, smooth event, but a series of escalating outbursts, with each subsequent ejection moving faster and sculpting the debris from the one before it. The driving force behind this cosmic fireworks display is the central star, a stellar remnant that is both incredibly hot and remarkably elusive. This nascent white dwarf has a surface temperature estimated to be a staggering 200,000 degrees Celsius, making it one of the hottest stars known. It is pouring out ultraviolet radiation with such intensity that it is rapidly eroding and ionizing the surrounding nebula, causing it to glow with a brilliance that belies its great distance. Yet, for a long time, the central star itself was notoriously difficult to observe directly, hidden behind the very thick walls of dust it helped to create. It's as if the star has built its own brilliant, opaque tomb while still residing inside it. This intense radiation is not just lighting up the nebula, it is also driving a powerful stellar wind, a stream of charged particles that is continuously shaping and compressing the inner regions, adding another layer of dynamic force to the system. Adding to the drama are the nebula's fast-moving, knotty jets. These are not the smooth, symmetrical outflows seen in some planetary nebulae. In NGC 7027, they appear as clumpy, bullet-like projectiles being fired from the polar regions of the central star system. Spectroscopic observations reveal these knots are moving at velocities exceeding hundreds of kilometers per second. Their formation is a subject of intense study, but the leading theory strongly points once again to a binary influence. The gravitational pull of a companion star could be essential for funneling and collimating the outflow into such focused, high-speed jets. These jets are plowing directly into the slower-moving inner shell, creating bright bow shocks and contributing to the nebula's overall lumpy, textured appearance. This constant assault from within ensures that the nebula is anything but a static monument. It is a chaotic construction zone, a place where the final form is still being violently negotiated between the central engine and the expanding debris. Perhaps the most surprising revelation about NGC 7027 came not from its visible structure, but from its chemical fingerprint. When astronomers began analyzing its spectrum, they expected to see the common signatures of hydrogen and helium, along with traces of elements like oxygen and nitrogen. They were not prepared for the chemical treasure trove they actually found. The spectrum of NGC 7027 is one of the richest known, revealing a veritable zoo of complex molecules and ions. It is abundant in carbon, making it a carbon-rich nebula, but the discoveries went far beyond that. Using powerful observatories like the now-retired NASA Infrared Telescope facility, scientists made the astonishing detection of buckyballs or Buckminster fullerenes. These are large, stable molecules consisting of 60 or 70 carbon atoms arranged in a hollow sphere, a molecular structure that resembles a microscopic soccer ball. Finding these complex carbon cages in space was a monumental discovery, suggesting that the conditions in expanding stellar envelopes are sophisticated chemical factories. The significance of this cannot be overstated. The detection of buckyballs, along with polycyclic aromatic hydrocarbons and other complex carbon compounds, shows that the violent death of a star is a prolific source of prebiotic material. These are the very building blocks that, in the right environment, could lead to the formation of even more complex organic molecules. The star that created NGC 7027 is essentially seeding the interstellar medium with the fundamental ingredients for future cosmic chemistry. This transforms our view of planetary nebulae from merely beautiful endings into crucial recycling plants. They are the primary mechanism by which elements forged in stellar cores, especially carbon, the backbone of life as we know it, are dispersed back into the galaxy. The iron in your blood, the oxygen you breathe, and the very carbon that defines organic chemistry were all created in stars and scattered by events like the one that formed NGC 7027. This young, dense, and brilliantly complex nebula is far more than the 50th strange object on our list. It is a vibrant, real-time snapshot of stellar death, a cosmic crucible forging the seeds of future worlds, and a profound reminder that from the end of one star comes the potential for countless new beginnings. Looking back across our journey through 50 strange and wondrous objects, a fascinating pattern begins to emerge. The sheer diversity, from the delicate lacework of the Veil Nebula to the monstrous black hole in NGC 1277, might seem like a random collection of cosmic oddities. But beneath the surface, these objects are all governed by a surprisingly small set of universal physical processes. They are not exceptions to the rules of the universe. They are the direct and spectacular consequences of those rules playing out in extreme environments. By stepping back, we can see three powerful, unifying themes that tie this entire cosmic menagerie together: the creative power of stellar partnerships, the profound influence of a galaxy's neighborhood, and the beautiful, violent cycle of matter that connects the death of one star to the birth of the next. The first and perhaps most dramatic theme is the role of binary stars as the master sculptors of planetary nebulae. For a long time, astronomers assumed that a single, dying star would naturally shed its atmosphere as a simple, expanding sphere. But as our catalogue has shown, very few of these nebulae are actually round. we have encountered butterflies, eyes, Saturns, and intricate spirals. The prevailing explanation for this stunning diversity almost always involves a second star. When a star has a close companion, its death is no longer a solitary event. It becomes a complex gravitational dance. The companion star's gravity can strip material from the dying primary, funneling it into a dense disk around the pair. This disk then acts like a nozzle, channeling the dying star's final, fast winds into two opposing jets. These jets blast into the slower-moving outer shell, sculpting the bipolar lobes we see in objects like the Butterfly Nebula and the Saturn Nebula. In cases like the cat's eye, a wobble or precession in this jet system over thousands of years can paint exquisite spiral patterns into the surrounding gas. The presence of a binary companion introduces an axis of symmetry, a preferred direction that breaks the perfect spherical symmetry of a lone star's death. It transforms a simple final breath into an elaborate, structured exhalation, proving that some of the universe's most beautiful art is the result of a dynamic and intimate partnership. The second unifying thread is the powerful influence of environment on galactic evolution. A galaxy is not an isolated island. Its life story is profoundly shaped by its surroundings, a concept often called environmental quenching. We see this starkly when we compare the chaotic, gas-rich irregularity of Barnard's galaxy, freely forming new stars in its isolated void, with the serene, red and dead majesty of the supergiant elliptical NGC 4889 at the heart of the crowded Coma cluster. In the dense urban centers of galaxy clusters, the rules of survival are brutal. The immense gravity of the cluster and the searing heat of the intracluster plasma effectively strip smaller galaxies of their cold gas, the raw fuel for star formation. This process, known as ram pressure stripping, leaves a galaxy unable to create new stars, dooming it to a quiet retirement filled with ancient red suns. Furthermore, in these crowded environments, galactic cannibalism is rampant. Giant galaxies like NGC 4889 grow to their immense sizes by consuming their smaller neighbors. Their smooth, featureless shapes are a direct result of digesting countless other systems. Meanwhile, in quieter galactic suburbs, a galaxy can hold onto its gas, leading to the vibrant, star-forming spirals like the archetypal NGC 1300. The ultimate form and fate of a galaxy are not determined by its birth alone, but by the gravitational tides and hostile winds of the cosmic neighborhood it inhabits. The third and most profound theme is the grand, cyclical nature of cosmic material, the constant recycling of matter from one generation of stars to the next. This cycle of star birth and death is the engine that drives the chemical evolution of the entire universe. It begins in colossal stellar nurseries like the Tarantula Nebula or the Lobster Nebula, where gravity collapses vast clouds of pristine hydrogen and helium. The most massive of these newborn stars live fast and die young, exploding as supernova within a few million years. In their spectacular deaths, like the one that created the Veil Nebula, these stars become cosmic forges. The incredible energy of a supernova explosion fuses lighter elements into heavier ones, oxygen, carbon, silicon, and iron, and then blasts them out across interstellar space. This enriched material, along with the gently expelled outer layers of smaller dying stars that form planetary nebulae like NGC 7027, then mixes with the surrounding gas. Over time, this newly seeded cloud, now rich in complex molecules and even the building blocks of life like the buckyballs found in NGC 7027, collapses once more to form a new generation of stars. But this new generation is different. It is born from material that has already been processed inside previous stars. This is why the ancient relic galaxy NGC 1277, which formed in a single early burst, has a different chemical signature than a modern spiral galaxy like our Milky Way, which has been continuously enriched by countless stellar deaths. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all created in the hearts of long-dead stars. Every strange nebula and every unusual galaxy we have explored is a single moment in this magnificent billion-year cycle. The universe is not a static collection of objects. It is a dynamic, breathing entity where the end of one star is the necessary precursor for the birth of another, and where the strangest objects are often the most vital links in the great chain of cosmic evolution. But the story of the new General Catalogue is far from a closed book, a relic of 19th century astronomy. This historic list, painstakingly compiled from visual observations, has found a breathtaking new lease on life in the 21st century, becoming a prime hunting ground for our most advanced observatories. The launch of the James Webb Space Telescope has fundamentally transformed our relationship with these cosmic landmarks. Its infrared eyes peer directly through the veils of dust that obscure the hearts of stellar nurseries and the cores of dying stars, revealing details that were nothing more than theoretical guesses just a decade ago. For instance, Webb's look at the Tarantula Nebula, NGC 2070, goes far beyond confirming its scale. It has resolved previously hidden protostars still in their dusty cocoons, allowing astronomers to literally count the newborn stellar population and measure their masses with unprecedented precision, testing theories about star formation in low metallicity environments that mimic the early universe. Similarly, when Webb turned its gaze upon the intricate Cat's Eye Nebula, NGC 6543, it didn't just see the concentric shells. Its spectrographs mapped the temperature and density of the gas in 3 dimensions, revealing the precise shock fronts where the fast winds from the central star collide with the slower-moving material. This data is helping to calibrate our models of mass loss, telling us not just how the star died, but the specific intensity and timing of its final, gasping breaths. This new wave of data is doing more than just filling in details. It is actively creating new puzzles. The Hubble Space Telescope's iconic image of the Lobster Nebula, NGC 6357, showed us the stunning pillars and the brilliant cluster Pisces 24. But when James Webb looked at the same region, its infrared vision detected a previously invisible population of much smaller, cooler, and fainter stars forming deep within those pillars. This forces us to reconsider the entire feedback process in such nebulae. How many of these diminutive stars will survive the relentless radiation from their massive neighbors? Are we witnessing the formation of an entire generation of solar systems that will be stillborn, their gaseous cradles evaporated before planets can even form? Webb's observations of planetary nebulae like the Saturn Nebula, NGC 7009, are revealing complex organic molecules like acetylene and benzene, frozen onto dust grains in the cold outer regions. Finding these building blocks of life in the expanding debris of a dead star was unexpected, suggesting that the chemical enrichment of the galaxy is even more sophisticated and widespread than we imagined. Each new observation with these modern tools adds a layer of clarity, but that clarity often reveals a deeper, more nuanced level of mystery, proving that these classic objects still have profound secrets to yield. The future of the NGC Catalogue is now inextricably linked to multi-wavelength and time-domain astronomy. It's not just about a single snapshot from one telescope, but about synthesizing data from across the electromagnetic spectrum and watching for changes over time. The Chandra X-ray Observatory continues to study the superheated gas halos around galaxies like NGC 4555, refining our understanding of dark matter's grip. The upcoming Vera C. Rubin Observatory will repeatedly scan the entire sky, and its powerful eye will not miss the NGC Catalogue. It will meticulously monitor variable objects like Hubble's Variable Nebula, NGC 2261, potentially catching the movement of individual dust shadows in real time. It will also hunt for the subtle, telltale flickering of stars in galaxies like NGC 1365, searching for the flares of tidal disruption events, the brilliant death cries of stars being shredded by the central supermassive black hole. This dynamic view transforms the static entries in the NGC from portraits into movies, allowing us to witness the universe as a living, breathing, and ever-changing entity. This historic catalogue, born from the patience of visual observers peering through brass and glass, has become a roadmap for the digital age of astrophysics. The 50 strange objects we have explored are no longer just curiosities. They are a calibrated set of cosmic laboratories. They provide the essential before images, the baseline against which we can measure, change, and test the most sophisticated computer simulations of stellar evolution, galactic dynamics, and black hole physics. The true promise of the NGC in the modern era lies in this continuity. It connects the astronomical endeavors of the past directly to the cutting-edge questions of the present, ensuring that the human drive to catalogue and understand the heavens will continue to illuminate the darkest and most wonderful corners of our universe for generations to come. And so our grand tour through 50 of the universe's most baffling and beautiful residents draws to a close. From the blinking ghost of Jupiter to the colossal black hole heart of a cannibal galaxy, from a star's final, frantic pulse to the delicate, spinning wings of a cosmic butterfly, we have witnessed a universe that is anything but static and serene. These objects are not mere anomalies, they are profound expressions of the fundamental forces that shape everything we see. They reveal a cosmos in constant flux, defined by dynamic relationships, the gravitational dance of binary stars, the violent mergers of entire galaxies, and the relentless cycle where stellar death directly fuels the birth of new worlds. This journey through the NGC catalogue has been more than a countdown of strange sights. It has been a masterclass in cosmic evolution, showing us that chaos and creation are two sides of the same coin, and that the most magnificent structures often arise from the most violent processes. The true wonder of this exploration is the realization that these distant enigmas are intimately connected to our own existence. The complex carbon molecules forged in the crucible of a dying star like the one in NGC 7027, the iron scattered by a supernova that created the Veil Nebula, the very oxygen we breathe, these are the elemental gifts from stellar lives long ended. We are not separate observers of this cosmic drama. We are active participants, our bodies made of atoms that were once scattered across the galaxy by the very kinds of cataclysms we have marveled at. The strange objects of the NGC are not just out there, they are a part of us, a permanent reminder of our deep and physical connection to the universe's grand recycling heart. This catalogue, started over a century ago with patient visual observations, has become a timeless bridge, connecting our innate curiosity to the cutting-edge discoveries of the James Webb Space Telescope and beyond, proving that the human drive to map the heavens continues to reveal deeper layers of mystery and wonder. This gallery of cosmic curiosities belongs to all of us, and the conversation is far from over. We would love to hear which of these 50 strange objects captured your imagination the most. Was it the haunting silhouette of the ghost of Jupiter, the impossible scale of the Tarantula Nebula, or the ancient relic mystery of NGC 1277? Share your own favorite cosmic mystery in the comments below and tell us why it fascinates you. The universe is a vast and strange place, and the journey of discovery is always better when shared. If you've enjoyed this deep dive into the celestial unknown and want to join us as we continue to explore the furthest reaches of space, from the mysteries of dark matter to the search for life on distant exoplanets, please subscribe to the channel. Thank you for embarking on this incredible journey through the cosmos. Keep looking up and never stop wondering.